Have you ever wondered what the very last moment of existence will look like? I don't mean with a bang, but with a slow, silent fade into absolute nothingness. See, everything that has a beginning has an end. Our lives, our planet, our star. And yes, even the universe itself. The story of the cosmos is this grand, epic tale that kicked off 8 billion years ago in a flash of pure, unimaginable energy. But like all good stories, it has to have a final chapter. Welcome to the Science for Deep Sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. So, come with me. Let's journey to the very edge of time and witness the final second of the universe. We're going to travel across trillions upon trillions of years, past the last flickers of dying stars, beyond the slow death of the mightiest black holes, and into an era so profoundly empty that the ideas of time and space start to unravel. This is the story of the universe's quiet, final moments, where reality itself dissolves into the cold, eternal darkness. Before we take that ultimate leap, we need to understand why the universe can't just stay in its vibrant, star-filled state forever. The answer boils down to two cosmic principles that are steering our fate: entropy and dark energy. First up is entropy, which is a core concept in physics, spelled out by the second law of thermodynamics. Basically, it says that everything in the universe tends to move from order to disorder. Think of a hot cup of coffee on your desk. Its heat doesn't just stay put, it spreads out into the cooler air until the coffee and the room are the same temperature. The energy is still there, but it's so spread out that it's useless. That's entropy. The entire universe is like that cup of coffee, constantly moving toward a state of perfect balance, where all energy is so evenly distributed that nothing interesting can ever happen again. It's a state often called the heat death of the universe. The second, and much more mysterious, force sealing our fate is dark energy. Back in the late 1990s, astronomers found something that completely blindsided them. They expected the universe's expansion, which started with the Big Bang, to be slowing down because of gravity. But they found the exact opposite. The expansion is accelerating. Galaxies aren't just moving apart, they're moving apart faster and faster every moment. This acceleration is chalked up to a bizarre force called dark energy, which acts like a kind of anti-gravity, pushing the very fabric of space-time apart. And it's not some minor player, it's the dominant force in the cosmos, making up about 68% of everything that exists. As space expands, matter and dark matter get diluted, weakening gravity's pull. But dark energy seems to be a property of space itself, so as more space is created, more dark energy appears, strengthening its outward push. This runaway expansion is what's driving the universe toward its cold, dark, and empty future. It's a one-way trip. Our journey to the last second is really a story told in great cosmic eras. We're living in the stelliferous era, the age of stars. But it won't last. It will be followed by the degenerate era, the black hole era, and finally, the dark era, where the final, lonely moments of reality play out. The end of the stelliferous era. The fading of the light. Just look up at the night sky. Every star, every galaxy you can see, is a monument to the era we live in, the stelliferous, or star-bearing, era. For the last 13 billion plus years, huge clouds of gas have been collapsing and igniting into the stars that light up the cosmos. Our Sun is one of them, a pretty average star holding our solar system together. But it's temporary. In about 5 billion years, it will run out of hydrogen fuel in its core. The core will shrink and heat up, causing the Sun's outer layers to balloon into a red giant, which will likely swallow Mercury and Venus, and maybe even scorch the Earth into a lifeless rock. After that, the sun will puff away its outer layers, leaving behind a glowing, Earth-sized ember called a white dwarf. Bigger stars live faster and die younger. They burn out in a few million years and go out in spectacular supernova explosions, leaving behind either super-dense neutron stars or black holes, points in space-time so warped that not even light can escape. But what about the real survivors? The most common stars in the universe are the red dwarfs. These little guys are cosmic misers, sipping their fuel so slowly that they can live for an almost unimaginable amount of time. While our sun will last about 10 billion years, a red dwarf can live for up to 10 trillion years or more. Fast forward with me to 100 trillion years from now. The stelliferous era is winding down. All the gas needed to make new stars has been used up. Star formation has completely stopped. The only lights left are the faint, ancient red dwarfs, the last holdouts of fusion in a darkening universe. Imagine floating in this future. The Andromeda Galaxy has long since merged with our Milky Way. But the other galaxies? They're gone. Not destroyed, but pushed away by the accelerating expansion of the universe. The space between our galaxy and all the others is expanding faster than light, meaning their light can never reach us again. To anyone left in our galaxy, the rest of the universe would look like a perfect, featureless void. The sky is now a vast darkness, pricked only by the dim, reddish glow of dying red dwarfs. For trillions more years, they're the only light in town. They'll watch as galaxies slowly fall apart, as stars are either flung out into the void or spiral into the supermassive black hole at the galactic center. And then, after a lifetime that makes the current age of the universe feel like a heartbeat, the very last red dwarf will use up its last drop of fuel. It won't explode. It will just fade out, slowly cooling into another white dwarf. With that, the last light from a star goes out. The stelliferous era is over. A profound, seemingly eternal night falls over the cosmos. We have entered a new age. The degenerate era, the age of cosmic corpses. We're now in the degenerate era, and it's basically a cosmic graveyard. The universe is populated only by the dead remains of stars, white dwarfs, neutron stars, and black holes. The timescale is now so mind-bendingly huge that years are useless. The universe is cold, dark, and silent. The stars of this era are the white dwarfs, which still glow with leftover heat for trillions of years before finally fading into black dwarfs. Cold, dead crystals of carbon and oxygen, like giant diamonds wandering the dark. Alongside them are neutron stars, the city-sized, ultra-dense cinders of supernovae. And of course, the black holes. For an almost impossible amount of time, this is it. A dark, empty space dotted with stellar corpses. But even these incredibly stable objects aren't forever. A new, purely theoretical process is predicted to take over: proton decay. While we've never seen it happen, some advanced theories predict that protons, the building blocks of atoms, are slightly unstable and can decay over immense timescales. The estimated half-life is at least 10 to the power of 34 years. That number is just staggering. But in the endless quiet of the degenerate era, time is one thing the universe has in abundance. And so, the slow-motion dissolution of all matter begins. Picture a black dwarf, a cold diamond the size of a planet, floating in the dark. Deep inside, a single proton spontaneously decays, releasing a tiny puff of energy. It's a microscopic event in an incomprehensibly vast emptiness. But it's a start. Across the cosmos, this happens again and again. One by one, protons vanish. Matter itself unravels. The black dwarfs, the neutron stars, every last rock and atom slowly evaporates into a thin mist of particles. By the time the universe is 10 to the power of 40 years old, it's over. All the protons are gone. Matter, as we know it, has ceased to exist. So what's left? The universe is almost completely empty, filled with a thin soup of photons, electrons, and other stray particles. The only things that survived are the black holes. They're immune to proton decay because they aren't made of matter in the normal sense, they're warps in spacetime itself. As the degenerate era ends, these silent, gravitational titans become the last kings of a dead universe. The black hole era. The last beacons of gravity. Welcome to the black hole era. The age of the universe is now around 10 to the power of -40 years, and this era will last for an even more absurdly long time. The cosmos is a near-perfect void, with the only organized structures left being the black holes. For a while, it seems like this must be the final state of reality. But it's not. In 1974, Stephen Hawking came up with a revolutionary idea that gave even black holes an expiration date. He realized that, thanks to the weirdness of quantum mechanics, black holes aren't completely black. They should actually emit a faint glow, now known as Hawking radiation. The basic idea is that empty space is filled with pairs of virtual particles that pop into existence and instantly annihilate each other. But if a pair appears right at the edge of a black hole's event horizon, one particle can fall in while the other escapes. To an outside observer, it looks like the black hole just spat out a particle. To conserve energy, the black hole has to pay for it by losing a tiny, tiny fraction of its own mass. This process is unbelievably slow. Right now, all known black holes are swallowing more cosmic radiation than they're giving off, so they're all growing. But in the deep freeze of the black hole era, there's nothing left to eat. The only thing happening is evaporation. A black hole with the mass of our Sun will take about 10 to the power of 67 years to evaporate. The supermassive ones at the centers of galaxies will last much, much longer. A really big one might take 10 to the power of 100 years, a number called a googol, to disappear. For a googol years, the only activity in the entire universe is the gentle hiss of Hawking radiation as the last organized objects slowly radiate themselves away. As a black hole shrinks, it gets hotter and radiates faster, until in its very final moments, it converts all its remaining mass into a brilliant flash of energy, a final, silent firework in the eternal night. One by one, from the smallest to the most gigantic, the black holes evaporate. And then, the last one goes. The black hole era is over. There are no more black holes, no stars, no atoms, no structure. Gravity, the grand architect of the cosmos, has nothing left to build with. The dark era and the last second. We've arrived. The final chapter. The dark era. The time is now 10 to the power of 100 years after the Big Bang. Words just fail here. What is the universe now? It's a near-perfect vacuum, colder and emptier than we can possibly imagine. Just a vast, ever-expanding void with a vanishingly thin soup of leftover photons, neutrinos, and electrons wandering in the infinite darkness, separated by distances larger than our entire observable universe is today. This is the heat death. The universe has reached maximum entropy. The temperature is a tiny fraction of a degree above absolute zero, and it's the same everywhere. There are no energy differences, so nothing can happen ever again. Even time itself becomes a strange concept. Time is measured by change. In a universe where nothing changes, does time even pass? It's a philosophical question that just hangs in the silent, timeless void. So where is the last second? Well, there isn't one. The end of the universe wasn't a single event. It was a process, a slow fade that took a googol years. The last event was the final flash of the last evaporating black hole. What follows isn't an event, it's a permanent, unchanging state of being. The last second is a poetic idea. It's the moment the story ended. The instant the last black hole vanished, leaving behind nothing but a quiet puff of radiation that will spread out into the void forever. We are now in the epilogue, and it stretches for an eternity. This is the most likely fate of our universe, based on everything we know. A slow, cold, and profoundly lonely end. The what-ifs, alternative endings. But what if our understanding is wrong? Cosmology is always evolving, and there are other, more violent ways this could all go down. The Big Rip. What if dark energy isn't constant? What if it's a phantom energy that grows stronger over time? If so, we could be in for a big rip. In this scenario, the accelerating expansion becomes unstoppable. First, galaxy clusters are torn apart. Then, galaxies themselves are shredded. A few months before the end, solar systems are ripped apart as gravity loses its grip. In the final minutes, stars and planets are disintegrated. In the last fraction of a second, the forces holding atoms together fail. Finally, spacetime itself is torn to shreds. The universe ends not with a whimper, but with an instantaneous and violent cataclysm. The Big Crunch. For decades, the Big Crunch was seen as unlikely. But recent results from projects like the Dark Energy Spectroscopic Instrument, (DESI), have revived the idea, suggesting that dark energy might actually be weakening. If that's true, gravity could eventually become the dominant force again. The expansion would slow, stop, and then reverse. The universe would start contracting, like the Big Bang in reverse. Galaxies would rush toward each other, merging and colliding in a universe getting smaller, denser, and hotter. In the final moments, everything would dissolve into a hellish furnace before collapsing back into an infinitely hot, dense singularity, the same state where it all began. According to some models, this could happen in around 20 billion years. This even opens up the tantalizing possibility of a big bounce, a new Big Bang erupting from the ashes of the old, creating an endless cycle of universes. Vacuum decay. And then there's the most terrifying possibility, one that could happen without any warning at all: vacuum decay. This idea stems from the Higgs field, the energy field that gives particles their mass. It's possible the Higgs field isn't in its true lowest energy state, but a false vacuum, like a boulder resting in a small dip on a mountainside, when there's a much deeper valley far below. Quantum mechanics allows for the boulder to spontaneously tunnel into that lower valley. If this happened to the Higgs field, a bubble of true vacuum would appear somewhere in the universe. Inside this bubble, the laws of physics would be completely different. This bubble would expand at the speed of light, destroying everything it touched. Atoms would fall apart. We would never see it coming. One moment, our universe is here; the next, it's gone, replaced by a new, utterly alien reality. It could happen in 1,000,000,000,000 years, or it could happen in the next 5 seconds. We've journeyed to the end of time and peered into the abyss. We've seen the slow, quiet fading of the Big Freeze, the violent tearing of the Big Rip, the fiery collapse of the Big Crunch, and the sudden, terrifying rewrite of reality in a vacuum decay. The ultimate fate of our universe is still one of the biggest unanswered questions in science. While the heat death seems to be the frontrunner, the recent hints that dark energy might be changing remind us that our cosmic story is far from over.
Whether the end is a cold whisper or a roaring inferno, the journey from the Big Bang to its final moments is a story of breathtaking scale. It's a story that has produced galaxies, stars, and on at least one little blue planet, a species able to look up and wonder where it all came from, and where it's all going. The timescales are so vast they make our entire civilization feel like less than a blink of an eye. And yet, in that brief moment, we have the profound privilege of being able to comprehend this cosmic drama. We are the universe made self-aware. And maybe that, in itself, is a kind of meaning that no amount of time or entropy can ever truly erase. What do you think is the most compelling, or maybe the most terrifying, end for our universe? Let me know in the comments. The long future of the cosmos. If the last second of the universe is hard to imagine, the long quiet road that leads to it may be even stranger. Because the end of reality does not begin with a dramatic collapse. It begins, instead, with an almost invisible thinning. A little less light, a little more distance, a little more silence between one star and the next. From where we stand now, the universe still feels full. The sky is crowded with stars. Galaxies are scattered through the dark like islands of fire. New suns are still being born inside cold clouds of gas. Planets are still forming. Heavy elements are still being forged in stellar cores and in the brief violence of supernova explosions. We happen to live in a very active chapter of cosmic history, a chapter where the universe still has fuel to burn and structure to build. But this chapter is not permanent. Long before the final darkness, long before the last black hole fades, the universe will begin a slow retreat from everything that makes it feel alive to us now. And in this part of our journey, that is where we are going. Not to the final instant yet, but to the unimaginably long era that comes before it. We are going to move through billions, then trillions, then tens of trillions of years, and watch the cosmos become quieter, colder, and more empty with every passing age. If you enjoy these slow walks through deep time, you can gently leave a like, subscribe if you haven't already, and if you feel like it later, tell me in the comments where in the world you're listening from tonight. There is something calming about remembering that many of us are lying awake under different skies, thinking about the same universe. For now, though, let us keep moving forward. At the moment, the universe is about 13.8 billion years old. That sounds ancient, and by human standards it certainly is. But on the scale of the full cosmic story, this may turn out to be more like an early middle than a true old age. We are living in what astronomers call the stelliferous era, the age of stars, when the universe is still able to transform gas into light. That process depends on a simple condition. The cosmos still contains large reservoirs of hydrogen and helium gas. Gravity can still gather that gas into clouds. And when those clouds become dense enough, their centers grow hot enough for nuclear fusion to begin. A star is born. Inside that star, gravity presses inward, fusion pushes outward, and for a while the two forces hold one another in balance. That balance is what makes a star shine. Every star is really a temporary agreement between collapse and radiation. Our own sun is living inside that agreement now. It is about 4.6 billion years old, roughly halfway through the most stable part of its life. For another 5 billion years or so, it will keep converting hydrogen into helium in its core, giving Earth the sunlight that has made oceans, weather, plants, and people possible. But even this familiar and reliable star is moving toward exhaustion. As the hydrogen in the core runs low, the sun will change. The core will contract. The outer layers will swell. Our quiet yellow star will expand into a red giant, growing so large that Mercury and Venus will almost certainly be consumed. Earth may be swallowed too, or it may survive only as a scorched and barren remnant, its oceans long gone and its surface melted and stripped beyond recognition. The exact details are still debated, but the overall picture is clear. The stable world that feels permanent to us is living on borrowed time. And yet, in the full future of the universe, the death of the sun is a very small event. Around the same broad span of time, roughly 4 to 5 billion years from now, another slow drama will unfold. The Milky Way and the Andromeda Galaxy, which are now drifting toward one another, will begin their long collision. It will not look like two solid objects smashing together. Galaxies are far too empty for that. Most stars will pass one another without direct impact. But gravity will reshape everything. Their spiral structures will stretch, twist, and dissolve. Gas clouds will collide and collapse. New waves of star formation may flare briefly from the chaos. Over time, the two great galaxies will settle into one larger system, sometimes nicknamed Milkomeda. It is a strangely beautiful thought. Long after Earth is no longer a home, long after the sun has changed beyond recognition, the stars of the Milky Way and Andromeda will still be arranging themselves into a new and unfamiliar sky. But even these large events belong to the relatively near future. If we keep traveling forward, a more important pattern begins to dominate the story. The universe is expanding, and that expansion is accelerating. This is one of the most important discoveries in modern cosmology. Galaxies are not simply moving apart because of an old explosion. Space itself is stretching. And because of dark energy, that stretching seems to be speeding up over time. The farther away a galaxy is, the faster it appears to recede from us. There will come a point when distant galaxies are carried so far away, so quickly, that their light can no longer reach whatever observers remain in our local region of the cosmos. This means that the future universe will not only be darker, it will also be lonelier. Give it enough time, and almost every galaxy outside our local gravitational neighborhood will disappear from view. Not because those galaxies are destroyed, but because the expanding universe will move them permanently beyond the cosmic horizon. Their light will redshift, weaken, and fade until they are effectively gone. To distant descendants, if any are ever there to witness it, the observable universe may seem to contain only one island of stars surrounded by endless blackness. The evidence for the Big Bang itself would become harder and harder to detect. In a very deep future, the cosmos could look static and empty to anyone who did not know its history. There is a haunting implication here for knowledge itself. Astronomers in that deep future, if there are any, may not see what we can see. They may live inside a single merged galaxy with no visible evidence that billions of other galaxies ever existed. The expansion of the universe, which is so central to modern cosmology, could become almost impossible to measure directly. The afterglow of the Big Bang would be stretched to wavelengths so long and signals so faint that it might slip beneath detection. In a strange way, the universe will not only become older, it will become harder to understand from the inside. That means we may be living in one of the best possible ages for doing cosmology. The universe is old enough for complexity, chemistry, and life, but still young enough to reveal its larger structure. We can still see distant galaxies. We can still detect the cosmic microwave background. We can still read traces of the beginning. Future observers may inherit a poorer sky, one that hides its own past. This may be one of the saddest details in all of cosmology. The universe will still be vast, but most of it will become unreachable and eventually unseeable. While this is happening on the largest scales, another process continues within galaxies themselves. Star formation slows down. It slows for a simple reason. The universe does not have an unlimited supply of cool, dense gas in the right places. Every time a new star forms, some of that raw material is used. Some is blown away by stellar winds. Some is heated so much that it becomes harder to collapse again. Some falls into black holes. Over immense stretches of time, the easy star-making fuel gets consumed or scattered. Galaxies do not stop making stars all at once. They simply become less fertile. You can think of the universe as beginning with a rich inheritance of gas and then gradually spending it. Right now, new stars still form in places like the Orion Nebula and in dense star-forming regions across many galaxies. But the cosmic birth rate is already lower than it once was. The universe was much more productive billions of years ago. There was a time known as cosmic noon, when star formation across the universe was near its peak. That peak is behind us. We are already living in a quieter cosmos than the one that came before. And the quiet will deepen. Massive stars burn their fuel quickly. They live bright and die young. A giant blue star can burn through its core in only millions of years, then explode as a supernova, leaving behind a neutron star or black hole. Sun-like stars last for billions of years. But the true long-term survivors are the smallest stars of all, red dwarfs. Red dwarfs are the misers of the cosmos. They shine dimly, but they spend their fuel with extraordinary patience. Some of them may live for trillions of years. Not billions. Trillions. Since the universe is not yet old enough for any red dwarf to have died of old age, all the red dwarfs that have ever formed are still out there, quietly burning. Their lives are so long that, compared with them, our sun seems almost reckless. As brighter stars disappear, red dwarfs will inherit the future sky. This changes not just the timeline of the cosmos, but its appearance. A future galaxy will not be lit mainly by stars like the sun. It will be lit, faintly and sparsely, by long-lived reddish stars, each one cool compared with our own, each one stretching out its existence across spans of time so large that entire civilizations, species, and worlds could rise and vanish many times over beneath their dim light. There is also the quiet question of planets. As stars age and environments shift, the number of comfortable, temperate worlds may decline. Around red dwarfs, planets can orbit close enough to be warmed by such small stars, but those worlds may be tidally locked, with one side facing permanent day and the other permanent night. Some could still host stable conditions, at least for a time, but the character of life around a future red dwarf would likely be very different from life on Earth beneath a sun like ours. Even habitability, like starlight, becomes more specialized as the universe grows older. If you could stand on a planet orbiting one of these late red dwarfs, far in the future, the sky might feel deeply different from ours. The great star fields we see now would be thinner. The large external galaxies would be gone from sight. The cosmic background radiation would be colder and more diluted. The heavens would not look like a young and busy universe. They would look old. This is the stage when the cosmos begins to resemble an aging city after midnight, when the bright central lights have gone out and only a few quiet windows remain. There is also another subtle process unfolding inside galaxies during these deep future ages. Stars do not remain neatly arranged forever. Over immense timescales, gravitational interactions slowly stir them. Passing stars tug on one another. Orbits shift. Some stars are thrown into intergalactic space. Others drift inward toward the dense central regions of merged galaxies, where supermassive black holes wait like dark anchors. Planetary systems can be disturbed. Entire worlds may be stripped away from their suns and sent drifting through interstellar darkness. The universe does not need explosions to become hostile. Time alone can do it. Picture a dead planet wandering between the stars, no sun to warm it, no dawn ever returning, only internal heat fading slowly beneath a frozen crust. Future space may be full of such worlds. Cold, silent, unlit. Not destroyed in any dramatic way. Simply left behind by the long rearrangement of gravity. And still the clock keeps moving. By around 1 trillion years from now, many galaxies will be much dimmer than they are today. New star formation will be rare. By around 10 trillion years, it will be rarer still. Over these incomprehensible spans, bright stars will have mostly come and gone. Their remnants will accumulate, white dwarfs, neutron stars, and black holes. The living population of stars will shrink toward the low-mass end. The universe will increasingly be dominated by old objects and slow processes. This is one reason the future is hard to imagine emotionally. Human beings are used to motion on the scale of hours, seasons, and lifetimes. Even geology already strains that intuition. Cosmology shatters it entirely. A single red dwarf may outlive not only humanity, but Earth, the Sun, the Milky Way's familiar form, and every currently visible galaxy beyond our local group. To such a star, nearly everything we call history would barely register. And yet, even red dwarfs are not forever. Because no matter how careful a star is with its fuel, fuel is still finite. A red dwarf can stretch its life to staggering lengths because it burns slowly and mixes its material efficiently, but eventually even that vast reserve runs down. Trillion after trillion years pass. The star grows dimmer, older, more altered by the fusion it has patiently sustained. Then, at last, it too reaches its end. Unlike massive stars, many red dwarfs do not die in spectacular explosions. Their ending is quieter. They simply exhaust what they can burn and fade into stellar remnants. The exact path depends on their mass and composition, but the broad emotional truth is the same. The longest-lived lights in the universe do not go out with fireworks. They go out with endurance. This means the end of the star-filled universe is not a sharp cutoff. It is a long dusk. There may be no single observer who can point to one instant and say, "This was the day the age of stars ended." It will feel more like watching a town lose power one house at a time over many centuries. At first, the darkness barely matters. Then it becomes noticeable. Then it becomes the defining fact of the landscape. By the time the universe approaches around 100 trillion years of age, the stelliferous era is effectively over. The easy age of starlight has ended. No fresh, ordinary stars are being born in meaningful numbers. The last red dwarfs, the final holdouts of nuclear fire, have done their work. What remains is a cosmos full of remnants. And that word matters, remnants. Because the future beyond this point is no longer shaped mainly by creation. It is shaped by leftovers. White dwarfs will cool for ages beyond ages. Neutron stars will remain as compact gravestones of ancient explosions. Brown dwarfs, which never became true stars in the first place, will drift in the dark like failed embers. Black holes will sit at galactic centers and in scattered regions of space, holding on to mass and memory in the only way black holes can. Even the brightest age of the universe will leave behind bones. If you listen closely, this is where the emotional meaning of the cosmic future begins to change. In the present era, the universe feels generative. It still makes things. It still surprises itself with birth. In the far future we are describing now, the universe becomes conservative. It spends more time preserving corpses than creating new lights. This is the threshold of old age on a cosmic scale. And yet there is a strange kind of peace in it too. The universe is not hurrying. Nothing about this decline is rushed. The road toward darkness is measured in stretches of time so large that they make our fears, deadlines, and ordinary worries feel like sparks from a match struck in a cathedral. The future cosmos is not angry. It is simply patient. That patience is what makes the journey unsettling and beautiful at once. Because when people imagine the end of everything, they often imagine a final disaster. A great tearing. A universal explosion. A moment of unmistakable catastrophe. But the most likely future, at least for a very long time, is much softer than that. The universe may not die in a single dramatic gesture. It may age. It may grow thin. It may grow cold. It may become a place where the distances between meaningful things become so great that even the word loneliness feels too small. And still, long before the true end, there is one last great image to hold on to. Imagine the final ordinary star still burning somewhere in the darkness. Not a giant blue sun. Not a brilliant supernova progenitor. Just a small red dwarf, dim and stubborn, carrying the final memory of the age when the universe still made light from hydrogen. Around it, the galaxy is mostly old. The bright generations are gone. The sky is emptier than any sky we have ever known. Beyond its local region, the rest of the cosmos has already disappeared behind expansion. And still that one small star shines. Then, after a life so long it almost defies language, it too fades. Not with fury. Not with a scream. Just with completion. When that happens, the long future of the cosmos crosses an invisible line. The universe moves out of the age of stars and into the age of stellar remains. The great lights have given way to ashes, crystals, collapsed matter, and black holes. The living heart of the cosmos has become a graveyard of its former fire. And that is where our next step will take us. Because once the last ordinary starlight is gone, the universe does not end. It becomes stranger. The dead begin to dominate the story. When the last star dies, the dead begin to dominate the story. That is the point we reached at the end of the last part, and it is worth sitting with for a moment, because it marks one of the quietest but most important changes in the whole history of reality. There was a time when the universe was defined by birth. Clouds collapsed. Stars ignited. Galaxies glowed. Heavy elements formed in stellar furnaces and spread outward into space. The cosmos was not still. It was productive. It was restless. It was full of new light. But nothing that depends on fuel can remain young forever. As the universe grows older, its energy does not vanish, but it becomes harder to use. The raw material for ordinary stars becomes more scarce. The brightest stars have already lived and died many times over. Even the long-lived red dwarfs, those patient little embers that seemed almost eternal beside the short lives of larger stars, are only delaying the same outcome. They are not escaping it. And so now we enter one of the strangest chapters in the future of the cosmos. We move toward the time when the last ordinary star will finally burn its final reserves and go dark. Not in a dramatic burst, not in a universal catastrophe, but in a way that is almost more unsettling because of how gentle it is. A fading, a completion, the end of the age of starlight. If you enjoy these long, quiet journeys through deep time, you can softly leave a like, subscribe if you want more of these calm science stories, and later on, if you feel like it, let me know in the comments what kind of sky you think would feel more haunting, one filled with countless bright stars, or one with only a single faint red sun left in all the darkness. For now, though, let us keep drifting forward. By the time the universe is tens of trillions of years old, it has already become a much dimmer place than the one we know. The great star-forming clouds that once filled galaxies like nurseries are mostly gone. Some of their gas has already been turned into stars. Some has been blown away by stellar winds and supernovae. Some has fallen into black holes. Some has been heated and spread out so thoroughly that gravity can no longer gather it as easily into new dense regions. The cosmos has not run out of matter, but it has run low on the kind of cold, concentrated material that makes star birth possible. This means the sky of the far future is not just emptier because stars have died. It is emptier because fewer new ones rise to replace them. There is a difference between a forest that loses trees but grows new ones, and a forest that has stopped regenerating altogether. The future universe is like the second kind. It still contains trees for a while, but their number only moves in one direction, down. Most of the brilliant stars are long gone by now. Massive blue stars had short lives from the beginning. They blazed fiercely and vanished early, some dying in supernovae, some collapsing into black holes. Sun-like stars lasted much longer, but even they have since passed into old age, swelling into red giants and shrinking into white dwarfs. The truly stubborn survivors are the red dwarfs, small stars with such modest appetites that they can keep shining for trillions of years. They are the final custodians of stellar light. If our sun is like a candle that burns through the night, a red dwarf is like a tiny coal that never seems to cool. It glows faintly, almost reluctantly, but it endures. And endurance is everything now. Imagine a galaxy in that remote future, though the word galaxy itself may already feel slightly wrong by then. The graceful spiral arms are gone. The elegant structure we associate with the Milky Way has long since been scrambled by ancient mergers, gravitational scattering, and the passage of time. What remains is a looser, older stellar population orbiting through a deeper dark. Many stars have been thrown out into intergalactic space over the eons. Others have slowly migrated inward. The supermassive black hole at the center is still there, silent and patient, but even it presides over a realm that has grown thinner and less alive. The light that remains comes mostly from red dwarfs, isolated and sparse. Their glow is weaker than the sun's, redder, quieter, more like an afterthought than a proclamation. If you stood on a surviving planet around one of these stars, the sky would not resemble our sky at all. There would be no dazzling band of the Milky Way stretched overhead. There would be no visible Andromeda in the distance. The great galaxies beyond the local gravitational neighborhood would have long ago slipped beyond the cosmic horizon, carried away by the accelerating expansion of space. Most of the universe would already be hidden forever. This is one of the eeriest parts of the story. Even before the lights go out, the stage itself begins to disappear. The deep future is not only darker, it is more isolated. The observable universe contracts in a practical sense, not because space grows smaller, but because more and more of what exists becomes unreachable and invisible. A future observer, if there ever is one, may live in a local island of ancient stars and black remnants with no evidence in the night sky that countless other galaxies ever existed. The universe will become harder to witness at the same time that it becomes harder to illuminate. And still the red dwarfs continue. Because they are fully convective, many red dwarfs mix their hydrogen efficiently. Unlike stars like our Sun, which burn hydrogen mainly in the core, red dwarfs can circulate material throughout much more of their interior. That means they use a greater fraction of their fuel. They are economical in a way that larger stars are not. They waste very little. Their entire structure seems designed for patience. Some of the smallest red dwarfs may live for up to 10 trillion years or even longer, depending on their exact mass. That number is so large that it almost stops feeling numerical and starts feeling geological, or mythic. 10 trillion years is around 1,000 times longer than the current age of the universe. It is a span of time wide enough to swallow every empire, every language, every ocean, every mountain, every memory of Earth, and still barely feel interrupted. During those ages, many quiet events continue to unfold. White dwarfs cool. Neutron stars drift. Black holes capture the occasional passing object. Gravitational encounters steadily reshape old stellar systems. Some planets are flung free of their stars and become rogues, wandering forever through the cold. Others spiral inward. Some may survive in stable orbits around dim suns for unimaginable lengths of time, orbiting beneath faint red light as the rest of the cosmos sinks into shadow. There is a strange tenderness in these late stars. Not because they are sentimental, but because they persist. They keep going after the universe has spent nearly all of its obvious beauty. When the grand star nurseries are gone, when the large external galaxies have faded from view, when the bright stars of youth have already burned themselves into cinders, these little red suns still endure, almost as if they do not know the age they live in. But of course they do know, in the only way a star can know anything. They know through structure, through pressure, through the gradual change in the chemistry of their interiors. Every second of fusion is a second less fuel to burn. Every patient turn of deep time brings them closer to completion. And the universe is in no hurry to stop them. If we continue moving forward, far beyond 10 trillion years, then 20 trillion, then 50, then 100 trillion, the population of shining stars becomes less and less like a society and more like a handful of scattered lanterns left on in abandoned rooms. Most are dim. Most are isolated. Most exist in environments where the sky is not rich with company but poor with absence. This is what makes the last star such a haunting idea. It is not merely the final member of a class of objects. It is the last ordinary source of steady, natural starlight anywhere in the cosmos. There is a temptation to imagine that moment as a clear and dramatic boundary, as if all physicists of the deep future could gather and point to a cosmic clock. But the real transition would likely be blurrier than that. The end of the age of stars is not a switch being flipped. It is more like a coastline disappearing in fog. At some point, you are no longer looking at a bright land receding into the distance. You are looking at open water. The difference comes gradually, then all at once. To understand how the last star dies, we should pause and ask what kind of star it is likely to be. It is almost certainly not something massive or blue or dramatic. Those stars live too fast. They would be long gone. It is also unlikely to be a star exactly like our Sun, because Sun-like stars simply do not last nearly long enough. The finalists in this cosmic marathon are the smallest hydrogen-burning stars, the dim red dwarfs that sip from their reservoirs so slowly that they can survive across stretches of time that make whole galaxies feel temporary. Over its life, such a star gradually transforms hydrogen into helium. Its brightness changes. Its internal balance shifts. Some models suggest that the smallest red dwarfs may slowly become slightly hotter and brighter over enormous timescales before moving toward their end. Unlike more massive stars, many do not swell into great red giants. They may instead evolve more quietly, eventually becoming degenerate remnants after exhausting the hydrogen they can fuse. That last phrase matters, exhausting the hydrogen they can fuse. Because stars do not die when time kills them directly. They die when the balance that defines them can no longer be maintained. A star exists because gravity is always trying to compress it while fusion-generated pressure pushes back. The star is a negotiation. When the terms of that negotiation can no longer be met, the object changes. For massive stars, that change can be explosive. For small ones, it is slower and quieter. But quiet does not mean insignificant. Quiet, in the future universe, is how even the biggest transitions happen. Picture, if you can, the final era when only a few scattered red dwarfs remain. The universe is now profoundly old. No bright galaxies blaze in the distance. Most stellar remnants are cold or collapsing. Vast numbers of black dwarfs and neutron stars drift through the dark. Planets, where they still exist, often circle failed suns, dead suns, or suns so dim that any warmth they give is meager and intimate. And somewhere in all this, one red dwarf is still burning. It may not even know it is the last. There is no cosmic registry. No universal signal is sent out to announce the final ordinary star. It simply continues doing what stars have done for almost the entire history of the cosmos. In its core, nuclei meet. Fusion happens. Energy rises outward. Light escapes. Time passes. Then one age later, it still shines. Another age later, it still shines. Then eventually, after a duration so vast that the word eventually seems absurdly small, it reaches the end of that possibility. Its fuel is no longer sufficient to sustain the same process. The inward pull of gravity begins to win the argument. The star changes state. The details depend on its mass, but the broad image is simple enough to hold. The final ordinary starlight in the universe fades into a remnant. There is no audience. There is no applause. There may not be any mind in existence to mark the event or give it meaning. And yet it is one of the most profound thresholds in the whole history of reality. Because once the last star goes dark, the universe loses something fundamental. Not merely a source of light, but a certain kind of activity. Stars are engines of transformation. They fuse light elements into heavier ones. They generate stable warmth over long periods. They create environments where planets can exist in energy-rich balance. They are the furnaces in which much of the ordinary chemistry of life becomes possible. When the last one dies, that whole style of cosmic creativity ends. After that, the universe is still not empty. But it is post-luminous in a new and deeper sense. There will still be flashes here and there, perhaps from rare interactions, from matter falling into black holes, or from exotic late processes. But the era when the sky is defined by stars is over. No new dawns. No old red suns patiently hanging on. No familiar stellar heartbeat continuing in the dark. Only remnants. This shift carries emotional weight even if nothing is there to feel it. There is something almost unbearably lonely in the thought that the universe could once have held hundreds of billions of galaxies, each with hundreds of billions of stars, and yet arrive, after enough time, at a stage where not one ordinary star remains. Such a future does not feel like a battlefield after war. It feels like a theater after the audience has gone home, after the final performance, after the lights have been switched off, and after even memory has started to leave the room. And still physics continues. This is important. The death of the last star is not the end of events. It is only the end of one kind of event. The cosmos still contains white dwarfs, neutron stars, brown dwarfs, rogue planets, stray particles, and black holes. Gravity still shapes orbits. Quantum effects still matter. Entropy still rises. Time, if we can still use the word comfortably, still moves through whatever changes remain possible. Some of those changes are astonishingly slow. White dwarfs, the hot Earth-sized embers left behind by stars like the Sun, cool for unimaginable lengths of time. At first they glow white, then yellow, then red, then eventually they radiate so little that they become black dwarfs, cold stellar corpses no one has ever seen because the universe is not yet old enough for one to exist. Neutron stars, the compressed remnants of supernovae, continue as ultra-dense relics, their matter packed so tightly that a teaspoon of it on Earth would weigh billions of tons. Brown dwarfs, not quite stars and not quite planets, drift like failed beginnings through the dark. And black holes, which will soon become the main characters of this future story, wait with a kind of terrible patience. But we are not there quite yet. For now, stay with the moment after the last star dies. What would the universe look like then? Not black in the simple way of an empty room with the lights off. It would be black in layers. Some objects would still glow faintly from leftover heat. Some would emit at wavelengths no human eye could see even if a human eye still existed. Some would be invisible except through gravity. Distances between objects would be enormous. The cosmic background radiation would have stretched further and cooled even more. The general texture of the universe would not be vibrant darkness punctuated by many lights. It would be dimness punctuated by the memory of light. Maybe that is the best phrase for it. The memory of light. Because after the final star, the universe does not instantly forget its brighter ages. It carries their remains. White dwarfs are the memory of sun-like stars. Neutron stars are the memory of ancient supernovae. Black holes are the memory of collapsed giants and devoured matter. Rogue planets are the memory of broken systems. Even the spread of heavy elements through space is the memory of long-dead stellar cores. The cosmos becomes an archive of processes that are no longer active. And archives have a quiet beauty of their own. There is also an interesting scientific subtlety here. In some models, rare collisions or interactions between stellar remnants might occasionally produce new bursts of light or temporary stars of a kind. For example, collisions between remnants in extremely rare cases could trigger brief renewed fusion or other energetic events. But these would not restore the ordinary star-forming universe. They would be isolated aftershocks, not a rebirth. The broad rule would remain unchanged. The era of normal stars would be over. That distinction matters for the tone of the future. It is not absolute stillness all at once. It is a deep and growing stillness with occasional exceptions that only prove how empty the background has become. If you imagine the universe as a song, then the age of stars is the long melodic section. The death of the last star is the moment that melody ends. Afterward, there may still be faint echoes, soft percussion, distant vibrations, but the main theme has finished. What remains belongs to a different movement entirely. And that movement is colder. It is older. It is ruled less by birth than by decay. This is one reason the final star is so symbolically powerful. It stands at the border between two kinds of universe. On one side is the cosmos we instinctively understand, a cosmos of suns, planets, warmth, and visible structure. On the other side is a universe increasingly dominated by remnants, by collapsed matter, by cooling objects, by black holes, and by timescales so stretched that language itself begins to feel flimsy. In that sense, the last star is not merely the end of a light source. It is the closing of a familiar chapter, a final line written in the alphabet of fire. Then comes the deeper dark. And the deeper dark is not empty of wonder. It is only wonder of a more severe kind. Because once the stars are gone, the objects left behind begin to shape the future in new ways. White dwarfs cool toward black dwarfs. Neutron stars continue their lonely existence. Atomic matter itself may face processes so slow and theoretical that they almost feel like whispers from mathematics rather than predictions about nature. And black holes, those dark wells in space-time that once seemed like the most final objects imaginable, will take center stage. But before we hand the story fully over to them, it is worth pausing one last time under the sky of the final star. Not because anyone will be there. Not because the star will know it is last. But because the universe, for nearly all of its life, has been a place where light was common enough to shape worlds and tell time by. There is something sacred in the thought that this condition had an ending, that even on the grandest scale, illumination was an age, not a guarantee. The last star shines. The last star endures. The last star fades. And after that, the cosmos belongs increasingly to the dead. In the next part, we move fully into that graveyard, into the age when black holes become the great lasting monuments of the universe, and when even they, impossibly, are not forever. The age of black holes. In the next part, we move fully into that graveyard, into the age when black holes become the great lasting monuments of the universe, and when even they, impossibly, are not forever. That is where we are now. The last ordinary star has faded. The familiar age of sunlight, of warm stellar systems, of bright galaxies dotted with countless living fires, has come to a close. What remains is older, colder, and much harder to picture, because the universe is no longer defined by what shines. It is defined by what endures. And among all the relics that survive into this astonishingly remote future, none are more enduring, more strange, or more quietly dominant than black holes. They were once the rare and mysterious endpoints of very massive stars. Then they became the hidden engines in the centers of galaxies. Later still, they outlived almost everything else. In the unimaginably old cosmos ahead of us, black holes are no longer exotic objects living at the edges of astronomy. They become the main architecture of what is left. They inherit the future not because they are active in the way stars were active, but because they are patient beyond anything else in the universe. If you enjoy these slow journeys through deep time, you can gently leave a like, subscribe if you want more calm science stories like this, and if the mood finds you later, tell me in the comments which future feels more haunting to you, a universe with one last dim star, or a universe ruled only by black holes. For now, let us keep moving into the dark. After the death of the last stars, the cosmos does not instantly become a kingdom of black holes alone. For a long time, it is more like an old museum of stellar remains. White dwarfs drift silently through space, still carrying some leftover heat from the ancient stars they once were. Neutron stars remain as collapsed cores, small and unimaginably dense, their matter squeezed into a state that sounds almost fictional until physics insists it is real. Brown dwarfs wander too, objects that never managed to become full stars at all. Rogue planets float in the dark between everything, stripped long ago from the systems that once held them. And then there are black holes, some born from stellar collapse, some much larger, sitting at the hearts of long-merged galaxies like dark anchors in an already dark sea. At first, this future universe is not empty in the strict sense. It is crowded with corpses. But the pattern has changed completely. There is no great cycle of renewal now. No clouds collapsing into brilliant new suns. No rich stellar nurseries spreading blue-white light across spiral arms. No cosmic dawns unfolding somewhere unseen. The energy is still present, but it is increasingly trapped, diluted, or locked into forms that do not lend themselves to fresh creation. The universe has become conservative. It holds onto what remains. This is the true beginning of cosmic old age. And old age, on the scale of the universe, does not arrive with a single date. It arrives as a change in character. The future becomes dominated by remnants rather than makers. The stars are gone. What is left is what they left behind. To understand why black holes rise to prominence in this era, we have to remember what a black hole really is. It is not a giant hole punched into space like an empty tunnel. It is an object formed when matter becomes so concentrated that gravity curves space-time into an extreme and inescapable shape. Around it lies the event horizon, the boundary beyond which even light cannot return. Anything that crosses that threshold joins the black hole's story, though from the outside, much of that story becomes hidden from view. Black holes can be very small by cosmic standards, only a few times the mass of our Sun, or they can be absolutely enormous, millions or even billions of solar masses, formed through repeated growth and mergers in galactic centers. In the present-day universe, they are already important. Many galaxies, including our own Milky Way, contain supermassive black holes at their cores. These immense objects influence the orbits of nearby stars and, during active phases, can power some of the brightest phenomena in the universe, such as quasars and energetic jets. But in the far future, black holes matter for a different reason. They are very hard to get rid of. Stars burn out because fusion depends on limited fuel. Planets cool because their internal heat leaks away. White dwarfs fade because they are embers, not engines. Neutron stars can survive for enormous lengths of time, but even they belong to the world of matter, and matter may not be perfectly eternal. Black holes, however, are not like ordinary objects. They are gravitational prisons made not of visible surface and interior in the familiar sense, but of space-time folded into an extreme shape. That makes them extraordinary survivors. So let us move farther forward. The universe is now far older than any number we use in ordinary life. Trillions of years have passed. Then many trillions. Then far more. The red dwarfs are gone. Their dim fires have ended. Around ancient galactic remnants, dead objects outnumber luminous ones by so much that the word outnumber hardly captures it. The background temperature of the cosmos has dropped further. Expansion has carried almost every structure beyond every other structure. Vast regions of space are effectively cut off from one another, separated not by solid barriers but by the endless stretching of distance itself. The sky, if sky is still the right word, has become almost featureless. And yet within the ancient wreckage of former galaxies, gravity still works. Remnants still drift and interact. Orbits still evolve. Slow scattering events still take place. Some dead stars are thrown out into deeper emptiness. Some spiral inward. Some collide. And in the central regions, black holes continue to gather what little comes near. This makes them, in a subtle way, the last large organizers in the universe. Not because they are building beautiful new systems, but because they still impose structure. Matter may have lost the ability to light up the cosmos as stars once did, but it can still fall. Gravity still has a language. And black holes speak it fluently. Picture an ancient merged galaxy long after its final starlight has gone. There is no shining spiral, no glowing nebula, no star-forming cloud, but there is still motion. White dwarfs drift through long elliptical paths. Neutron stars move like compact bullets through the dark. Brown dwarfs wander. Black dwarfs, the cold remnants of once hot white dwarfs, begin to populate the old stellar graveyard. And somewhere in the core sits a supermassive black hole, vast, invisible, and calm. Every so often, a remnant comes too close. Its orbit destabilizes. It is captured or torn apart. A final brief release of energy may flare and vanish. Then the darkness settles again. This is not a lively universe. But it is not yet still. In fact, one of the most interesting things about the age after stars is how much can still happen when time is generous enough. Processes that seem impossibly rare in our present universe become almost inevitable when given spans of time large enough. A close pass between two stellar remnants may take longer than the current age of the universe to occur, and yet in the old cosmos, it happens. A compact object may be nudged from a stable orbit after countless gravitational encounters, and after wandering for ages, it eventually finds its way toward a black hole. Nothing happens quickly, but quickness is no longer the standard. There is something deeply calming, and a little unsettling, about that. The universe has become a place where patience replaces drama, where futures unfold not because something explodes, but because enough time makes even unlikely outcomes normal. As these eras continue, the balance among the remaining objects slowly changes. White dwarfs cool further. Neutron stars remain dense and severe. Black dwarfs accumulate. More matter falls into black holes, especially in the crowded centers of old galactic remnants. Black holes also merge with one another from time to time. When two black holes spiral together and combine, they produce gravitational waves, ripples in spacetime itself. In our present era, detectors like LIGO have already heard the faint echoes of such mergers from across the universe. In the future, those mergers may continue, but with fewer observers and a much darker backdrop. Imagine, if you like, a pair of black holes orbiting one another in a region where no ordinary star has shone for ages beyond counting. There is no light show, no colorful explosion, only a tightening dance governed by pure gravity. Over immense time, they spiral inward. They merge. Spacetime trembles. Then a single larger black hole remains, even more dominant than before. This is how the future becomes consolidated. Small things are lost, scattered, cooled, or consumed. Large gravitational structures become simpler and harsher. But there is another reason black holes come to rule the cosmos, and it has to do not only with their endurance, but with the possible fragility of everything else. Some grand unified theories in physics suggest that protons, the building blocks of atomic nuclei, may not be perfectly stable forever. No one has ever observed proton decay directly, and if it happens on timescales so vast that they make even stellar lifetimes look brief. We are speaking here about at least 10 to the power of 34 years, and likely much longer. It is a number so large that the mind almost gives up trying to hold it. And yet, if protons really do decay, then the matter making up planets, white dwarfs, black dwarfs, and even neutron stars may not survive indefinitely. The atoms themselves would slowly come apart. Not all at once, of course. There would be no visible collapse in the ordinary sense. A black dwarf would not crack open dramatically in the dark. A neutron star would not suddenly explode because one proton failed. The process would be so sparse and so slow that, for almost all of its existence, the object would seem unchanged. But across absurdly long spans of time, those microscopic changes would accumulate. Matter would leak away. Structure would unravel. The old corpses of stars would eventually dissolve into thinner and thinner seas of particles and radiation. This possibility changes the emotional character of the future even more, because it means the universe is not merely moving away from life and warmth and light. It may be moving away from ordinary matter itself. If proton decay is real, then the reign of white dwarfs, neutron stars, and black dwarfs is only temporary. Long though it is still an era of transition. The dead stars do not become the final permanent furniture of the universe. They become yet another phase that the cosmos passes through on its way to something even emptier. And black holes, once again, stand apart. They are not made of matter in the same simple sense. They are not held together by chemical bonds or atomic nuclei. Whatever else may happen to the particles scattered across the old universe, black holes remain. They continue to curve spacetime. They continue to collect what little wanders too near. They continue, by sheer stubbornness, to inherit time. This is why the age we are entering can rightly be called the age of black holes. Not because they are the only things left immediately after the stars die, but because once the other remnants fade, cool, decay, scatter, or dissolve, black holes become the clearest surviving form of organized cosmic structure. It is a strange victory. In the age of stars, power belonged to brightness. The greatest objects were those that illuminated worlds and forged elements. In the age of black holes, power belongs to silence. The greatest objects are those that trap, persist, and outlast. There is something almost poetic in that reversal. The universe begins with light bursting outward and ends, at least for a long while, under the rule of the darkest things it ever made. Let us move farther still. The timescales now become so remote that even phrases like ancient galaxy feel too small. Many former galactic structures have unraveled under repeated gravitational interactions. Stars that once orbited in stable arrangements have long since been scattered or consumed. Expansion has carried isolated systems away from one another beyond all practical contact. Matter between the last major black holes has grown sparse. The cosmic background radiation has stretched to longer and colder wavelengths. The whole universe feels thin, like a once rich fabric pulled almost to transparency. And in that thinning cosmos, black holes remain as the last deep wells. A stellar mass black hole may drift alone through a volume of space so huge that the nearest substantial object is unimaginably far away. A supermassive black hole may sit at the center of a dark remnant that no longer resembles a galaxy in any luminous sense, only a loose halo of cold leftovers moving through regions of utter blackness. Nothing about this is vivid in the ordinary visual way. It is grand through absence, through scale, through the contrast between the simplicity of what remains and the complexity that used to exist. It is also here that black holes begin to feel almost like monuments. Not monuments in the human sense, carved to remember a past, but monuments in the sense that they are the last enormous signatures left behind by vanished ages. A black hole in the far future is not just a gravitational object. It is a record of everything that fed it. Ancient stars, ancient gas clouds, ancient mergers, ancient galaxies. Every meal it ever swallowed is hidden in its mass. In a way, a black hole is the compressed memory of cosmic history, stripped of detail but not of consequence. That memory, however, is inaccessible. Black holes preserve, but they do not tell stories back to us. Information enters, but for any external observer, it is hidden behind the event horizon. This is part of what makes them so eerie. They are both archives and silences. They contain history without narrating it. By this era, if there were any surviving observers, their universe would be almost impossible for us to emotionally recognize. There would be no sunrise, no ordinary night sky, no richly populated galaxy overhead. Even nearby objects might be cold and invisible except by their gravitational effects. The most significant bodies would be dark. The future would not look like a more extreme version of the present. It would look like the present after almost everything we associate with normal cosmic life had been edited away. And yet, black holes themselves would still seem timeless. That is the illusion they give. Because black holes appear so absolute that they feel like endpoints. When something falls in, it does not come back. When a star collapses into one, it seems to have crossed into a final category. It is easy to imagine black holes as the universe's last unchanging masters, objects that will remain long after all else has gone. For a long time, this almost seems true. If you were standing conceptually at a point in cosmic history where matter has mostly decayed, where stars are gone, where old remnants have thinned out, where the universe has expanded into near emptiness, you might reasonably think the story is over. The last major actors remain. The gravitational wells are still there. The future looks static, terminal, complete. But the universe is not done surprising us. Because black holes are not eternal either. Not in the deepest sense. That revelation belongs to the next stage of the story, and it is one of the strangest in all of physics. It tells us that even the darkest, heaviest, most inescapable objects in the cosmos are slowly leaking away. Not through any ordinary process of erosion or collision, but through quantum mechanics itself. Through the restless weirdness of empty space. Through a phenomenon so subtle that it would have seemed impossible before Stephen Hawking showed that it should exist. For now, though, stay in the age before that final loss becomes the main event. Stay in the reign of black holes. A universe with no stars, no new creation, no great visible structures, and yet not fully gone. A universe where the last monuments are invisible except by the gravity they cast into the dark. A universe where time stretches so far that patience becomes the only way to think. A universe old enough that even the word old feels young beside it. Black holes rule this era because they are the best survivors the cosmos ever produced. But survival, in the end, is not the same as permanence. And in the next part, we will step into one of the quietest and most astonishing endings in all of science. The moment when even black holes begin, impossibly slowly, to disappear. The last black hole, survival, in the end, is not the same as permanence. That is the quiet truth waiting for us now, and it may be one of the strangest truths in all of physics. Because by the time the universe reaches the deep age of black holes, it feels as though the story should already be over. The stars are gone. The galaxies, as we once knew them, have unraveled into old remnants and darkness. Ordinary matter has thinned, cooled, drifted, and perhaps even begun to decay. Black holes remain as the final monuments of gravity, the deepest wells in a universe that has otherwise grown almost empty. And yet even they do not last. Not forever. Not for all the time the universe still has left. If that sounds impossible, that is because black holes seem designed to be the most final objects nature can make. They swallow light. They resist escape. They endure after almost everything else has failed. They look, from the outside, like the endpoint of all collapse. The place where matter, motion, and history go to disappear. But the deeper we look into nature, the more the universe seems to dislike perfect endings. Even the darkest object is not perfectly dark. Even the most final prison is not perfectly sealed. Empty space itself has secrets in it. And those secrets are enough, over a long enough time, to wear down a black hole until nothing is left. If you enjoy these calm journeys through the far future, you can softly leave a like, subscribe if you want more slow science stories to drift off to, and if you feel like it later, tell me in the comments which ending feels stranger to you, the death of the last star, or the death of the last black hole. For now, let us stay here in the deepest old age of the cosmos and watch the darkest things in existence begin, almost imperceptibly, to fade. To understand how a black hole can disappear, we first need to let go of one comforting instinct. The instinct is this, that empty space is really empty. In daily life, that sounds reasonable. If you remove the air from a container, if you take away dust, gas, and light, then what remains feels like nothing. An emptiness. A vacancy. But quantum physics does not treat empty space as a blank stage. Even the vacuum has activity in it. Even the emptiest region of the universe is restless at the smallest scales. According to quantum field theory, what we think of as empty space is filled with fluctuating fields. Tiny temporary disturbances can appear and vanish. One common way of describing this is to speak of virtual particle pairs, little pairs of particles and antiparticles that briefly emerge from the vacuum and then annihilate one another almost immediately. That picture is a simplification, but it captures the important feeling. The vacuum is not dead. It seethes quietly. And near a black hole, that quiet restlessness begins to matter in a very unusual way. In the 1970s, Stephen Hawking combined ideas from quantum mechanics and general relativity and arrived at a remarkable result. Black holes, he showed, should not be perfectly black. They should emit radiation. Very faintly, very slowly, but truly. Over time, that radiation carries away energy. And because energy and mass are equivalent, the black hole loses mass in the process. This is what we now call Hawking radiation. It remains one of the most famous predictions in modern theoretical physics because it takes something that appears absolute and reveals it to be temporary. A black hole is not just a one-way trap. It is also, on incomprehensibly long timescales, a leaking object. There are different ways to explain Hawking radiation, and some are more accurate than others, but for our calm walk through the far future, the intuitive image is enough. Imagine the region near the event horizon, the boundary around a black hole beyond which no return is possible. Quantum fluctuations there can behave differently than they do in ordinary empty space. One simplified picture is that a particle pair appears near the horizon. One falls inward, the other escapes. To a distant observer, it looks as though the black hole has emitted a particle. But it cannot do this for free. The escaping particle carries energy away, and the black hole pays for it with a tiny bit of its own mass. That is the essential idea. A black hole, left alone long enough, slowly evaporates. Now, if you hear the word evaporates, you might imagine steam rising from a kettle or water disappearing from a puddle after rain. But Hawking radiation is nothing like that in any ordinary visual sense. It is unbelievably faint for large black holes. A stellar mass black hole, one formed from the collapse of a massive star, radiates at a temperature far colder than the cosmic microwave background of our present universe. Right now, such a black hole absorbs more energy from the surrounding universe than it emits. It is not shrinking. It is gaining, or at least not yet losing in any meaningful way. Only in the much deeper future, when the universe has expanded and cooled almost beyond imagination, does the balance shift. Once the background radiation falls below the temperature of the black hole begins to lose more than it gains. From that point on, if nothing significant falls in, it starts a slow decline. And slow really is the word. A black hole with roughly the mass of our Sun would take something like 10 to the power of 67 years to evaporate. That number is so huge it scarcely belongs to speech. It is a 1 followed by 67 zeros. Compared with it, the current age of the universe, 13.8 billion years, is less than a whisper. And supermassive black holes, the giant ones once found in galactic centers, survive much, much longer still. A black hole with billions of times the Sun's mass may endure for around 10 to the power of 90 or even 10 to the power of 100 years, depending on its size and history. A Google years. It is one of those rare times in science when the formal number and the poetic feeling behind it are equally overwhelming. A Google is not just a large number. It is a number so large that it feels like a test of whether the human mind was ever meant to think this far. And yet this is the timescale on which the end of black holes unfolds. Picture the universe now. Not the universe of galaxies and starlight. Not even the universe of dead stars crowding ancient galactic ruins. Picture a cosmos so old that most ordinary matter is gone or diffused into thin seas of particles. Picture temperatures near absolute zero. Picture distances stretched almost beyond meaning. In this black, quiet immensity, the last great structures are black holes. Some are relatively small, perhaps the long-lived remnants of ancient stellar collapse. Others are vast beyond comparison, built from old mergers, from swallowed stars, from consumed gas, from the history of whole galaxies compressed into darkness. They drift in isolation or sit at the centers of dark relic structures. Nothing like a visible civilization remains to mark them. No bright sky surrounds them. No ordinary orbiting worlds remain warm enough to care. All that remains is gravity and time. And time, in the age of Hawking evaporation, becomes the only real weather the universe still has. Over these absurd spans, a black hole emits radiation with perfect patience. A little energy escapes. Then more, far later. Then more again. Not in a steady dramatic stream, but in a process so sparse that if you tried to watch it in the ordinary sense, it would seem indistinguishable from stillness. Ages would pass with almost nothing to notice. The black hole would sit there, dark and immense, and yet mathematically it would be very slightly lighter than before. There is something deeply eerie about that, not because it is violent, but because it is so quiet. The final destruction of the universe's most durable objects is not carried out by force from the outside. It is carried out by the quantum restlessness of empty space itself. A black hole is eroded by the vacuum, and as it loses mass, something interesting happens. It gets hotter. This is the reverse of what we often expect. For ordinary objects, more mass can mean more heat content, more capacity to hold energy. But black holes obey stranger rules. The larger a black hole is, the colder it is. The smaller it becomes, the hotter it gets. So the evaporation process does not merely continue at one constant rate forever. It accelerates. For nearly all of a black hole's life, the loss is so slow that it barely seems real. But toward the end, as the black hole becomes smaller and hotter, the radiation intensifies. The process speeds up. The last fraction of its lifespan is far more active than the first vast eons. This means every black hole has two personalities. The first is the long, silent endurance that can outlast stars, galaxies, and possibly matter itself. The second is the final flare, the sudden quickening, the brief last burst as the object spends its remaining mass in a rush of radiation. Even here, the universe preserves a kind of dramatic instinct. After all that patience, the end comes faster. Let us move through this era carefully. The smaller black holes go first. Any black holes with less mass evaporate sooner, since they are hotter to begin with and lose energy more rapidly. That means the universe does not lose all its black holes at once. It loses them in a long hierarchy. Small ones fade first. Larger ones follow. The biggest remain until almost everything else that can happen has already happened. In a way, it echoes the history of stars. The largest stars lived fast and died young, while the smallest stars endured. But with black holes, the rule turns inside out. The biggest black holes endure the longest. The giants inherit the deepest future. Imagine one of the last stellar mass black holes. It has survived for a period of time that would make all stellar history look like a brief prelude. There are no normal stars left to feed it. No nearby gas clouds. No glowing accretion disk. It is alone in a region of space so empty that even emptiness feels crowded compared with what surrounds it. Yet over time, it shrinks. Unimaginably slowly, but truly. Its horizon contracts. Its temperature rises. Its radiation becomes less negligible. Eventually, after its impossible age, it reaches its final moments and converts what remains of its mass into a burst of energy. Then it is gone. No body remains behind. No cold cinder. No invisible core. The black hole has ended not by crumbling, not by collision, but by disappearing into radiation. Now multiply that image across the future. One by one, over spans too large for language to hold comfortably, black holes vanish. Ancient stellar remnants of collapse. Mid-sized merged black holes. Intermediate giants. Then, after far longer still, the supermassive black holes. The supermassive ones are perhaps the most haunting of all, because they are not merely objects. They are the final condensed records of old galaxies. The black hole once at the center of the Milky Way, Sagittarius A star, is only a few million solar masses. The one in Andromeda is much larger. In the merged future galaxy of our local group, new mergers and accretion may produce an even more massive central black hole. On larger scales elsewhere in the young universe, even more enormous black holes formed, containing billions of solar masses, maybe more. In the far future, after galaxies are gone as visible structures, these giant black holes remain as their final hidden hearts. And even they evaporate. Think of what that means. A black hole built from the deaths of stars, from the collisions of galaxies, from the long memory of cosmic structure, can spend nearly a Google years outlasting everything around it and still, in the end, dissolve into thin radiation. The future does not preserve monuments forever. It only delays their erasure according to size and patience. There is a melancholic kind of fairness in that. Nothing is exempt. Not stars. Not planets. Not matter. Not black holes. If the universe has a habit, it may be this one, to let things endure just long enough to seem eternal before quietly proving otherwise. And then there is the last black hole. Of all the images in the future of the universe, this may be one of the most arresting. Because once there is only one black hole left, the entire architecture of the old cosmos has reduced to a single final gravitational monument. No stars. No galaxies. No clusters. No meaningful matter structures. Just one black hole, somewhere in a universe stretched so thin and cold that the idea of location itself begins to feel fragile. This last black hole will almost certainly be enormous, the product of every prior advantage in the cosmic contest of endurance. It may have begun in a galactic center. It may have merged with others over impossible spans. It may carry in its mass the hidden remnants of stars, gas clouds, and dark epochs beyond count. It is the champion of persistence, the last great survivor. And yet, by then, survival no longer means safety. For all around it, there is only vacuum and time. Nothing substantial is left to fall in and replenish it. The background universe is too cold and too empty. Hawking radiation continues its work. The black hole loses mass, at first so slowly that whole imagined civilizations could rise and vanish in the interval between meaningful changes. Then less slowly. Then faster. Its temperature climbs. Its horizon shrinks. Its final age approaches. What would it be like to witness such a thing, if witnessing were somehow possible? The answer is almost impossible to phrase, because ordinary sensory language breaks down here. There is no bright scenery around it, no nearby starfield for contrast, no familiar space environment, only a dark horizon against deeper darkness, perhaps with increasingly energetic radiation emerging from the final phase of evaporation. It would not look like a fire in a forest. It would look like the last ember in a universe that forgot what forests were. Then comes the end. As the black hole becomes tiny, its temperature becomes enormous. The radiation intensifies drastically. The last remaining mass is converted into a final pulse of energy, a burst far more active than the long ages of silence that came before. After such immense patience, the conclusion is brief. The last black hole flashes. And then the universe crosses another threshold. Because once the last black hole is gone, gravity no longer has any major structures left to organize around. There are no more deep wells in space-time built from collapsed matter. No more horizon swallowing history. No more great monuments of darkness remaining from the luminous ages of the past. The final kings of the old universe have left the stage. What remains after that is difficult to describe because it is no longer a universe of objects in the ordinary sense. It is a universe of leftovers, thin radiation, sparse particles, cold emptiness. Distances so enormous that almost nothing meaningfully interacts with anything else. The last black hole does not merely mark the death of one kind of object. It marks the end of structure at the highest surviving scale. This is why its disappearance matters so much in the larger story. The end of the last star was the end of ordinary light. The end of the last black hole is the end of the last great organizer. Afterward, the universe is no longer old in the way a city is old, with ruins and monuments and surviving architecture. It becomes old in the way ashes are old. There may still be pieces. There may still be traces. But the forms that once held history together have vanished. There is also a philosophical strangeness here that is hard to avoid. If time is usually measured by change, then what does time become in a universe after the last black hole? The evaporation itself is a kind of final event, a last meaningful punctuation mark in the long sentence of cosmic history. Once it passes, there may still be fluctuations, still particles, still expansion, but the pace and significance of change become so diminished that the future feels less like a narrative and more like an endless condition. The last black hole is perhaps not the end of time, but it does feel like the end of almost everything time used to do. And still, one detail makes the whole picture even more haunting. The end is not a single universal instant visible from everywhere. The universe is too large and too relativistic for that simple notion. There is no cosmic clock hanging above reality that strikes midnight for all things at once. The last black hole is last in a broad physical sense, the last major structured gravitational object to evaporate. But the story remains local, relative, scattered across immense space-time. Even at the end, the universe refuses to give us a neat center. That may be why the phrase "the last second of the universe" feels so poetic. Nature does not owe us a final chime. It gives us processes, thresholds, and eras. The death of the last black hole is one of those thresholds, and perhaps the closest thing the universe has to a final grand gesture before slipping into an even deeper quiet. By then, the age of stars is a forgotten brightness. The age of galaxies is an inaccessible memory. The age of black holes is over. The long reign of the darkest things has ended, not with collision, not with reversal, but with the whispering persistence of quantum physics. Empty space wins. Or perhaps not wins. Perhaps simply continues. And that is where our journey takes us next. Because after the last black hole flashes into nothing, the universe enters a state so thin, so cold, and so nearly featureless that even the word empty begins to feel inadequate. It is here that we reach the deep meaning of heat death, the point where energy still exists, but useful differences are gone, structure is almost absent, and reality itself begins to feel less like a story than a silence stretched across forever. In the next part, we step into that silence. Heat death. In the next part, we step into that silence. And silence, out here, is no longer just the absence of sound. It is the absence of contrast, the absence of structure, the absence of all the familiar imbalances that once made the universe feel alive. The last black hole has faded. Its final pulse of radiation has dispersed into the dark. Gravity no longer rules through great wells of collapsed matter. The stars are gone. The galaxies are gone in every meaningful, visible sense. Even the black holes, those last stubborn monuments of cosmic endurance, have surrendered to time and quantum physics. What remains is something stranger than destruction, because destruction at least feels active. What remains now is a condition. A universe that has not exploded, or collapsed, or been torn apart in one dramatic gesture, but has simply reached the point where almost nothing useful can happen anymore. This is what physicists mean when they speak of heat death. It is one of the most haunting ideas in science because the phrase sounds violent, yet the reality behind it is almost unbearably gentle. Heat death does not mean a fiery ending. It means the opposite. It means the universe has become so cold, so even, so thoroughly worn smooth by time, that there are no meaningful energy differences left to power change in the ways we normally understand it. Energy still exists. It has not vanished. But it is spread too thin, too evenly, too uselessly. The cosmos has become like a machine whose battery is not empty, but whose charge is smeared so uniformly across everything that nothing can turn on. If you enjoy these slow journeys into deep time, you can gently leave a like, subscribe if you want more calm science stories to fall asleep to, and if you feel like it later, tell me in the comments what sounds more unsettling to you, a universe that ends in one final catastrophe, or one that simply grows too quiet for anything meaningful to continue. For now, let us stay with the quiet and try to understand what it really means. To understand heat death, we need to return to one of the simplest and most profound ideas in all of physics, entropy. Entropy is often described as a measure of disorder, and while that is not a complete definition, it is a useful place to begin. More carefully, entropy tells us something about how energy is distributed and how many ways a system can be arranged. Systems tend to move from states that are organized, uneven, and useful towards states that are more spread out, more probable, and less capable of doing work. You can see a tiny version of this in everyday life. Imagine a hot cup of tea sitting in a cool room. At first, there is a strong difference between the tea and the air around it. The heat in the tea can flow outward. Over time, the tea cools and the room warms by an immeasurably tiny amount. Eventually, both reach roughly the same temperature. At that point, the energy is still there. It has not disappeared. But the difference is gone. No more heat naturally flows from one to the other. The original imbalance has been erased. That is the essential mood of entropy. The universe, on the largest scale, behaves in much the same way. Early on, there were enormous gradients, dense regions, hot regions, empty regions, collapsing clouds, burning stars, growing black holes, expanding space, and all the structural differences that make interesting things possible. Stars shine because their interiors are much hotter and denser than the space around them. Planets have weather because energy from a star hits one side more than another and is redistributed. Life exists because it feeds on gradients. We eat because there is a useful difference between food and waste, between stored chemical energy and released chemical energy. Engines work because one place is hotter than another, one pressure is higher than another, one state is less probable than the next. Interesting things happen where differences exist. Heat death is what the universe looks like after almost all those useful differences have been erased. That idea can feel abstract at first, so it helps to approach it gently. The future universe after the last black hole is not literally nothing. It is not a blank void without particles, without photons, without any trace of physics. There are still things. There are still fields. There is still expansion. There may still be isolated particles and incredibly long wavelength radiation moving through the dark, but there is almost no structure left that can usefully change other structure. No stars are burning. No matter is falling into black holes. No large warm objects are cooling against colder backgrounds in any interesting way. No galactic centers are organizing motion. No chemistry is blooming on a warm world. The cosmic cup of tea has reached room temperature, except the room is the whole universe. And the room is almost perfectly cold. There is something important here that can be easy to miss. Heat death does not require absolute zero. In fact, the universe may never reach absolute zero in a strict sense. What matters is not that every particle has literally no motion, but that the temperature becomes so low and so uniform, and the remaining energy so diffuse, that no free energy is left to drive large-scale processes. Free energy is the part that can do work. Once that is gone, the difference between having a tiny amount of energy and having none at all starts to matter less. Functionally, the universe is finished. This is why heat death is often described as the maximum entropy state of the cosmos. Maximum entropy does not mean that every possible thing has happened. It means the universe has settled into a condition where nothing large or organized can continue to unfold in the old ways. It has reached the most probable broad arrangement, the one toward which so many earlier processes have been leaning from the beginning. Not through intention, not through purpose, just through statistics and time. And time, by now, has had more than enough opportunity to do its work. Try to picture the future after the last black hole again. Not as a dramatic landscape, because there is almost nothing left to decorate it with. Picture instead a vast expanding space-time filled with an incredibly thin soup of low-energy particles and radiation. The distances between meaningful encounters are so great that chance interactions become almost absurdly rare. The wavelengths of leftover photons have stretched enormously with the expansion of the universe. The overall temperature has dropped and dropped and dropped. Every reservoir of concentrated energy that once powered stars, planets, galaxies, and black holes is gone. There is no cosmic fireplace left. No bright center. No source of asymmetry grand enough to build a world around. This is the point where heat death begins to feel less like a scientific term and more like a philosophical atmosphere. It is not just the death of stars or the evaporation of black holes. It is the death of usefulness. The death of available potential. The death of those uneven conditions that allowed complexity to emerge against the backdrop of the dark. In the living universe, matter was always falling, colliding, igniting, cooling, gathering, scattering, and transforming. In the heat-dead universe, the great drama of transformation has run out of stage directions. Of course, on paper, tiny things may still happen. Rare collisions between stray particles could occur. Quantum fluctuations may still exist. Expansion continues. If protons do not decay, some isolated matter might remain for inconceivably long times. If they do decay, even less ordinary matter survives. Either way, the broader truth remains. The cosmos is no longer a place of meaningful macroscopic becoming. It has entered a condition of almost total thermal and structural exhaustion. This is one reason the heat death scenario feels so powerful for sleep and for contemplation. It does not frighten us by speed. It frightens us by stillness. By the idea that the universe does not need to be shattered to end. It may simply need to become too even, too spent, too quiet to continue telling new stories. And this possibility is not just poetic. It follows naturally from the two great themes we have already been walking with since the beginning of this journey: entropy and expansion. Entropy tends to spread energy out. Expansion makes the distances between things larger and larger, reducing the frequency and significance of interactions. Together, they push the universe toward dilution and isolation. Stars die because fuel is finite. Black holes evaporate because quantum physics will not let them remain perfectly closed forever. As the universe expands, even the leftover radiation stretches and cools. Every chapter of cosmic history seems to spend a little more of what made the previous chapter possible. The future becomes a long accounting of exhausted differences. And yet, if we slow down and look carefully, there is something almost serene in the image too. A universe in heat death is not raging. It is not in agony. It is not collapsing in confusion. It is simply done. There is a dignity in that kind of ending. A profound stillness. The universe is no longer struggling to build structure or hold it together. The long contest between gravity, fusion, radiation, quantum fluctuation, and expansion has moved beyond the age of monuments. All the bright arguments are over. The cosmos is no longer trying to become something. It has become the most evenly worn version of itself that physics permits. In human life, we often fear endings because they feel like interruption. A heat-dead universe does not feel interrupted. It feels completed. That may be what makes it eerie. When people first hear the phrase heat death, they sometimes imagine the universe turning into a kind of cosmic freezer. And in one sense, that is not entirely wrong. The future is cold. Very cold. The cosmic background temperature continues to fall as space expands. But the deeper meaning is not coldness alone. It is uniformity. A universe at a slightly non-zero temperature everywhere, but with almost no gradients, is more dead in the thermodynamic sense than a colder universe with one remaining star would be. A single hot star in a cold cosmos can still power change. A perfectly even mild temperature everywhere cannot. Life, motion, and work all feed on imbalance. When the imbalance goes, so does the possibility of almost everything we care about. This invites another strange question. If heat death is the maximum entropy state, is it permanent? For ordinary physical intuition, the answer seems to be yes. Once the universe is this spread out, this thin, this uniform, there is no obvious path back. Thermodynamics strongly favors movement toward higher entropy, not away from it. A spilled glass does not gather itself back onto the table. A cooled room does not spontaneously reheat the tea. The statistics are overwhelmingly one-sided. On fantastically long timescales, people sometimes discuss whether tiny fluctuations in a heat-dead universe could produce local oddities, rare temporary decreases in entropy, perhaps even bizarre spontaneous structures. These ideas belong to the deeper philosophical and statistical edges of cosmology, and they are fascinating. But they do not rescue the ordinary universe. They do not bring back galaxies, stars, or the familiar architecture of cosmic history. At most, they suggest that even near total stillness may not be mathematically perfect in every detail forever. Yet the broad condition remains one of exhaustion. The universe we have known is over. There is another reason heat death feels so emotionally complete. It is the point where matter and energy are no longer arranged in ways that preserve memory at scale. Think about what memory requires. It requires structure. A brain, a book, a computer, a planet with geology, even a black hole carrying hidden information behind a horizon. All of these are arrangements. They are patterns that distinguish one state from another. They are records held in form. A heat-dead universe is a universe that has largely run out of meaningful form. That means it has, in a deep sense, run out of memory. The young universe remembers itself through galaxies. The middle-aged universe remembers itself through stars and planets and life. The old universe remembers itself through black holes and remnants. The heat-dead universe barely remembers anything at all. Only the most diluted traces remain, smeared across space-time so evenly that the past no longer stands out from the background in any way that matters. And this, perhaps, is where the phrase "the last second of the universe" becomes most poetic. Because in strict physics, heat death is not 1 second. It is not a single event, not a universal bell ringing midnight everywhere at once. It is a state approached over unimaginable durations. The last black hole evaporating may be the closest thing to a final punctuation mark. But heat death is the long silence after the punctuation. It is the epilogue that never ends. There is no one instant where the universe flips from alive to dead in a neat cinematic way. Instead, there is a long fading of processes, a long removal of contrast, a long erosion of usable energy, until eventually one can say that whatever used to make the cosmos feel active has been worn below significance. This may actually be truer to how endings work in reality. Not with one loud sound, but with thresholds crossed so quietly that only in hindsight do they seem absolute. Another unsettling detail waits here too. In a heat-dead universe, time itself starts to feel difficult to interpret. Physically, time can still be described. Equations can still carry a variable forward. Expansion can still continue. A particle can still drift. A wavelength can still stretch. But in the ordinary human sense, time is intimately tied to change. We notice time because things happen. Light moves across a room. A face ages. Water boils. A planet turns. A civilization rises and falls. We tell time by comparison, by process, by regularity. When almost all significant processes have faded into near nothing, time remains, but its texture changes. A universe with almost no events is a universe where time becomes thin, not absent. Thin, like a river so broad and slow that from the shore it looks like a pane of dark glass. This is why some philosophers and physicists speak carefully around the end state. If nothing meaningful changes, what does it mean to say that an eternity passes afterward? Eternity relative to what? Counted by what clock? Against what background of events? Time may still exist in the formal sense, but it no longer feels inhabited. That may be the loneliest part of heat death. Not just that the universe is empty or cold, but that it becomes event-poor enough that even time seems to lose its ordinary companionship with becoming. And still, there is one more layer to the beauty of the idea. Because the heat-death scenario is, in a quiet way, deeply democratic. It does not single out one place for destruction and spare another. It does not end through local violence. It is the gradual leveling of everything. The stars do not die because they were weak. The black holes do not evaporate because they failed. Worlds do not freeze because they did something wrong. The universe as a whole simply obeys the rules built into it from the beginning. Energy spreads. Expansion continues. Differences fade. Structure becomes rarer. Complexity becomes harder to sustain. In the end, everything joins the same stillness. That kind of ending can feel sad, but it can also feel strangely gentle. The universe is not punished. It is not betrayed. It is not torn apart in anger. It simply becomes smooth. If you imagine the full history of the cosmos as a piece of music, then heat death is not the final crash of cymbals. It is the final note stretched thinner and thinner until it disappears into the room, and the room itself has become so vast that the difference between sound and silence is almost impossible to tell. That is the deep quiet we have now reached. No stars. No black holes. No engines. No warm worlds. No great centers of gravity. Only a thin sea of leftover existence drifting through expanding darkness. And yet, even here, the story of how reality might end is not finished. Because heat death may be the most likely ending under our current understanding, but it is not the only ending physicists have imagined. There are other possibilities, other futures in which the universe does not merely cool and flatten into silence. In some of them, the expansion grows violent. In others, it reverses. In others still, the very vacuum beneath reality may be unstable. So as we rest here for a moment, at the quietest edge of the most gentle ending, hold on to this feeling. The sense of a universe that did not die through one final battle, but through completion, through balance, through the patient removal of every useful difference. Because from this stillness, we can now compare it to more dramatic fates. And in the next part, we turn toward one of the most violent possibilities of all, a future in which space itself does not merely carry things apart, but eventually tears galaxies, stars, planets, atoms, and perhaps reality itself into pieces. The Big Rip. From this stillness, we can now compare it to more dramatic fates. Because heat death is quiet. It is patient. It is the kind of ending that arrives by subtraction, one difference at a time, until the universe no longer has the contrast it needs to keep making interesting things. But not every possible ending is so gentle. There are other futures physicists have imagined, and some of them do not drift into silence at all. Some of them break. One of the most unsettling of these possibilities is known as the Big Rip. Even the name feels sharp compared with the calm language of heat death. It sounds less like old age and more like tearing cloth. Less like a fading story and more like a page being pulled apart with both hands. And in a sense, that is exactly what it means. The Big Rip is the idea that the expansion of the universe may not simply continue forever at a steady accelerating rate. It may become stronger and stronger over time, until the force driving space apart eventually overwhelms every other force in nature. At first, that sounds almost too dramatic to be real. Space itself pulling galaxies apart is already strange enough. But space pulling solar systems apart, then planets, then atoms, then perhaps spacetime structure itself, sounds like a nightmare invented to make cosmology feel crueler than it already is. And yet the idea comes from a serious place. It begins with dark energy, the same mysterious influence we met near the beginning of this journey, the one that seems to be driving the accelerating expansion of the cosmos. If you enjoy these slow and unsettling walks through the future of reality, you can softly leave a like, subscribe if you want more calm science stories like this, and if you feel like it later, tell me in the comments which feels more haunting to you, a universe that fades into silence, or a universe that is slowly pulled apart from the inside. For now, let us stay very still and look carefully at how the Big Rip would work. To understand the Big Rip, we need to return to a simple observation that changed cosmology forever. In the late 1990s, astronomers studying distant supernovae found evidence that the universe was not merely expanding, it was accelerating. Galaxies were not just drifting apart with leftover motion from the Big Bang. The rate at which space expanded between them appeared to be increasing. This was astonishing because gravity should, in the ordinary picture, slow expansion down. Matter attracts matter. Galaxies pull on one another. On the largest scales, you might expect the universe to keep expanding for a long time but with a gradually weakening pace. Instead, observations suggested that some large-scale effect was pushing the cosmos in the opposite direction. We gave that effect a name, dark energy. The name, of course, is not an explanation. It is a label for a mystery. We do not know exactly what dark energy is. It may be a property of empty space itself, something like Einstein's cosmological constant. It may be tied to quantum vacuum energy in some way we do not yet fully understand. It may be evidence that our theory of gravity is incomplete on the largest scales. But whatever its ultimate nature, it seems to act, in broad terms, like a kind of anti-gravity on cosmological distances. That is already enough to produce a universe that grows emptier over time. Distant galaxies cross beyond the cosmic horizon. The future becomes colder and more isolated. That much fits comfortably within the heat-death picture. But the Big Rip requires something more severe. It requires dark energy not to remain constant, but to become dominant in an ever more extreme way. In some speculative models, dark energy is not simply a fixed property of space. Its effective strength grows as the universe expands. The technical language often involves something called the equation of state parameter, which describes how pressure relates to energy density. In the simplest cosmological constant model, that value sits at a particular balance that produces acceleration without any wild escalation. But if the value drops below a critical threshold, what physicists call phantom energy, then the behavior changes in a dramatic way. Instead of dilution making the universe calmer, expansion makes the dark energy effect stronger. And if that happens, then the future stops being a slow dispersal and becomes a countdown. That is the real horror of the Big Rip. Heat death is an asymptotic ending. The universe approaches it more and more, with no sharp universal deadline that matters in ordinary emotional terms. The Big Rip, by contrast, implies a finite final time, a genuine endpoint. Not necessarily a single clock visible to everyone everywhere, but a real cosmic limit beyond which the current form of spacetime cannot continue. If the Big Rip is correct, then the universe is not merely aging. It is heading toward a tearing event. The reason this becomes so violent is that the expansion of space is not like an explosion pushing objects outward from a center. It is the stretching of space itself. On the largest scales, galaxies move apart because the fabric between them expands. Under normal circumstances, this does not tear apart smaller bound systems, because local forces are stronger. Gravity holds galaxies together. Gravity holds solar systems together. Electromagnetism holds atoms and molecules together. Strong nuclear forces hold atomic nuclei together. These local structures ignore the expansion because the binding forces inside them are far more powerful than the weak stretching of cosmic space across those tiny scales. But in a Big Rip universe, the stretching does not stay weak. It intensifies. And if it intensifies enough, then one boundary after another begins to fail. The whole future becomes a hierarchy of things being unbound. At first, the process would not feel dramatic in the ordinary human sense. The earliest stages would resemble an exaggerated version of the future we already discussed under heat death. Distant galaxies would recede faster and faster. More of the universe would disappear beyond the cosmic horizon. The night sky would empty. The observable cosmos would shrink to a smaller and smaller island. That part, in a way, would look familiar. But then the acceleration would keep increasing. Galaxy clusters, those enormous groupings of many galaxies bound together by gravity, would begin to come apart. The space between their members would expand too strongly for the cluster's gravity to hold them in one shared structure. Galaxies that once orbited within the same great cluster would drift beyond one another's reach. Then individual galaxies themselves would begin to fail as gravitational systems. This is one of the most haunting images in the whole scenario. Because galaxies feel stable to us. They feel ancient and architectural. The Milky Way is not a fragile cloud in our imagination. It is a vast rotating city of stars, a spiral structure so immense that even light takes about 100,000 years to cross it. Yet in a Big Rip universe, there comes a time when even a galaxy is no longer strong enough to stay itself. The stars begin to drift free, not because they explode, not because they collide, but because the fabric of space between them expands with such insistence that the collective pull of the galaxy can no longer keep them in orbit. What was once a coherent spiral or elliptical structure becomes a loosening swarm. Then not even that. The galaxy is unmade, one orbit at a time. Imagine a night sky in such an age, if there were anyone left to see it. The grand band of the Milky Way would fade not because stars have died, but because the galaxy itself has stopped being a galaxy. The familiar arrangement would dissolve. The stars nearest you might remain for a while, still bound by local gravity. But the larger structure would be gone. And still the expansion would keep strengthening. This is what makes the Big Rip feel so merciless. It does not stop once the large structures are erased. It keeps descending through scales, like a crack moving through thicker and thicker layers of reality. After galaxies come solar systems. For most of cosmic history, planets are held to stars by gravity with quiet reliability. Earth circles the Sun. The Moon circles Earth. The architecture is stable because the gravitational bonds are strong relative to the small effects of cosmic expansion on those scales. But in the final stages of a Big Rip universe, that assumption fails. The outward stretching of space becomes large enough to overcome the bond between star and planet. Planets drift away from their suns. Not because their stars explode. Not because they are struck by anything. Simply because the structure of space no longer allows their orbits to remain closed. Gravity loses the tug of war. A world that once knew years and seasons would leave its sun behind. In some estimates from phantom energy models, this stage happens surprisingly close to the final end. On cosmic scales, very close. The unbinding of galaxies might occur millions of years or more before the final rip, while solar systems could fail much later, perhaps only months before the end, depending on the exact model. The details vary, but the emotional shape stays the same. The approach to the Big Rip is not uniform. The larger structures go first. The smaller, tighter systems hold out longer. Reality gives way layer by layer. There is something terrifyingly intimate about that. Because heat death leaves local worlds alone for a very long time before the broader background swallows meaning. The Big Rip comes all the way down to the scale of home. It does not merely take the distant galaxies from your sky. It takes the orbit of your planet. It takes the planet itself. It takes the chemistry of matter. If the acceleration continues to rise, then after solar systems come planets. The gravitational self-binding of a planet, the thing that keeps it together as one world instead of a cloud of separated pieces, would no longer be enough. A planet would be pulled apart by the expansion. Mountains, oceans, crust, mantle, core, all would cease to belong to one coherent body. Then the same logic continues. Moons separate from planets. Planets separate into debris. Stars themselves are disrupted. Then molecules lose their integrity. Atoms are torn apart. Electrons are no longer held near nuclei. And if the model is extreme enough, even nuclei themselves may not survive. By the final instant, spacetime itself may be in a condition no ordinary object can meaningfully inhabit. This is why the Big Rip feels less like death and more like disassembly. The universe is not ending because it has run out of useful gradients. It is ending because the very stage on which matter arranged itself has become violently unstable for all structure. At this point, it helps to pause and remember something important. The Big Rip is not the leading expectation under the simplest current cosmological models. It belongs to a family of speculative possibilities based on what dark energy might be if it behaves in a more extreme way than a cosmological constant. That does not make it fantasy. It makes it conditional. If dark energy has this more dangerous character, then the future is not a slow fade but a tearing. If it does not, then the universe may head toward a gentler end, like heat death. That uncertainty is part of what gives the Big Rip its special atmosphere. It is not a certainty, but a possibility living inside the mystery of dark energy. And dark energy remains one of the deepest mysteries we know. We can measure its large-scale effects. We can describe the expansion of the universe. We can fit models to observations. But the underlying nature of the phenomenon is still hidden from us. We do not yet know whether dark energy is fixed, evolving, emergent, or a clue that something even more fundamental in gravity must be revised. So the Big Rip remains like a shadow at the edge of the map, not the best traveled road, but one we cannot fully erase. There is also another reason this scenario feels so powerful in the imagination. It reverses one of the oldest instincts we have about size and strength. Usually, we think the small is fragile and the large is enduring. A house survives longer than a cup. A mountain survives longer than a tree. A galaxy feels more secure than a planet. But in the Big Rip, endurance depends on how tightly a thing is bound, not how grand it looks. The largest structures fail first because they are the most weakly held on a per-distance basis. Clusters go before galaxies. Galaxies go before solar systems. Solar systems go before planets. Planets go before molecules. Molecules go before atoms. The final survivors are not the grandest. They are the most tightly stitched. And even they do not survive forever. Let us imagine the final approach more slowly. Suppose there is some observer in a universe headed toward a Big Rip. Long before the last stages, most of the visible cosmos has already vanished beyond the horizon. The observer sees a smaller universe than we do. Then even the local galaxy begins to dissolve. The broad structure of the sky changes. Stellar neighborhoods thin and drift. If there are any surviving worlds, their astronomy becomes sadder and smaller year by year, though year may already be the wrong emotional unit for what is happening. Much later, as the final phase is near, the observer's own system becomes unstable. The home star no longer anchors the planets securely. Orbits distort. Separation grows. The sky changes not over eons now, but over smaller and smaller intervals. Familiar distances cannot be trusted. Gravitational relationships that seemed eternal begin to fail. Then the world itself becomes vulnerable. At that stage, the language of cosmology and the language of catastrophe overlap. Because a planet torn apart by cosmic expansion is not a metaphor. It is the failure of the most basic large-scale coherence of matter. Then smaller scales. Then smaller still. What would it feel like? That question is almost impossible to answer cleanly because by the time local structures fail, the ordinary conditions for any observer to persist have already become absurdly hostile. But in a poetic sense, the Big Rip is the universe losing its ability to hold things together at every level. It is not just the end of places. It is the end of belonging. No object belongs to itself any longer. No orbit belongs to a system. No galaxy belongs to its stars. No atom belongs to its own shape. That is why the Big Rip often feels more emotionally terrifying than heat death, even if heat death may be more likely. Heat death says the universe grows too quiet to continue. The Big Rip says the universe becomes too unstable to remain assembled. One is a fading. The other is an undoing. There is another subtle philosophical difference too. Heat death still allows the universe to keep existing afterward in a thin, exhausted state. The Big Rip feels more terminal. If the expansion becomes literally infinite in finite time, then the mathematical future of the cosmos reaches a singular boundary. We are no longer speaking only of old age, but of an edge in the evolution of spacetime itself. That word edge matters. Because one of the deep emotional needs behind all these end-of-the-universe scenarios is the question of whether reality has a final page. Heat death gives us an endless epilogue. The Big Rip gives us something closer to a last line. And maybe that is why it grips the imagination so strongly. A final line is easier to fear. Of course, nature is under no obligation to give us the ending style we find most dramatically satisfying. The universe will not choose between poetry and cruelty for our benefit. It will do what its underlying laws permit. But part of the reason cosmology is so beautiful is that these possibilities reveal different personalities hidden within the same basic reality. A universe ruled by stable dark energy ages into silence. A universe ruled by phantom dark energy tears itself apart. The ingredients are similar. The fate is radically different. It is almost like two versions of old age. In one, the cosmos grows tired. In the other, it grows unstable. And there is one more haunting twist to the Big Rip. Because unlike heat death, where the destruction of structure happens mostly through exhaustion, the Big Rip would come while useful structures still existed. It would not wait for the last stars to die naturally, or the last black holes to evaporate. If dark energy grows strong enough quickly enough, it interrupts the normal sequence of cosmic aging. In that sense, the Big Rip is less an ending after completion and more an ending by force. The book is not finished. It is torn in half. That may be why the scenario feels like such a violation. It does not merely conclude reality. It cancels it. And still, as frightening as it sounds, there is a kind of cold elegance in the logic. The same expansion that already carries galaxies apart would simply continue becoming more important until every other force loses. There is no need to invent a new substance at the last minute. No need for a supernatural trigger. The Big Rip is what happens if one quiet trend in cosmology never stops intensifying. A small acceleration becomes a cosmic verdict. That, too, is worth sitting with. Because so many great changes in nature begin in ways that look harmless or subtle at first. A star spends billions of years in apparent stability until its core chemistry shifts. A black hole seems permanent until quantum physics reveals a leak. The universe expands for billions of years, and only later do we realize that the expansion is accelerating. If the Big Rip were true, then hidden inside that already strange acceleration would be the seeds of total disassembly. There is a calm terror in that idea. Not because it is loud, but because it is mathematical. A future written quietly into the behavior of space. And yet for all its violence, the Big Rip is not the only dramatic alternative to heat death. There is another possibility, almost the mirror opposite. in which the universe does not fly apart ever faster, but eventually slows, stops, and reverses. Instead of everything being dragged outward into more emptiness, everything is pulled back inward. Instead of a tear, there is a collapse. If the Big Rip is reality unbinding itself, the next possibility is reality falling back into itself. And in the next part, we turn toward that opposite fate, the Big Crunch, the idea that the universe may one day stop expanding and begin the long journey home into fire, density, and final compression. The Big Crunch. If the Big Rip is reality unbinding itself, the next possibility is reality falling back into itself. It is, in a way, the opposite kind of nightmare. Not a universe that expands too hard and tears everything apart, but a universe that cannot keep escaping its own gravity forever. A universe that stretches outward for ages, slows, hesitates, stops, and then begins the long return inward. Galaxies that once drifted away would begin moving back toward one another. The dark would brighten again, not because the cosmos is becoming young, but because it is becoming crowded. Space would shrink, density would rise, temperature would climb, and everything that once spread outward from the Big Bang would, in this vision, begin to gather itself into a final collapse. This possibility is known as the Big Crunch. It has a very old and powerful hold on the human imagination because it feels symmetrical. There is something almost mythic about the idea that the universe began in a hot, dense state and may one day end by returning to one. A great outward breath followed by an equally great inhale. Expansion followed by reversal. Creation followed by compression. It sounds like a cosmic circle, or at least the beginning and end of one. If you enjoy these quiet walks through impossible futures, you can gently leave a like, subscribe if you want more slow science stories like this, and if you feel like it later, tell me in the comments which feels more haunting to you, a universe ripped apart into nothing, or one pulled back into a final fire. For now, let us keep going, and step into the strange possibility that everything may someday come back together. For a long time, the Big Crunch was one of the most natural endings cosmologists imagined. The logic was simple enough. The universe is expanding, yes, but gravity pulls matter together. If there were enough matter in the universe, then perhaps that expansion would gradually slow down. If it slowed enough, perhaps it would stop. And if it stopped, then perhaps gravity would take over completely and reverse the motion. The universe would begin contracting. In that older picture, the whole story depended on a kind of cosmic contest between motion and mass. The Big Bang provided the outward movement. Gravity provided the inward pull. The future depended on which one ultimately won. If the density of the universe was high enough, gravity might be strong enough to halt the expansion and bring everything back. This is why cosmologists often spoke in terms of geometry and density. A universe with too little matter would expand forever. A universe with enough might be closed, meaning that its large-scale structure and gravity would eventually lead to recollapse. There was a certain elegance in that way of thinking. It made the future feel like the answer to a single question asked at the beginning. Was there enough in the universe to bring itself back? But as observations improved, especially in the late 20th century, that old picture became more complicated. The discovery that cosmic expansion is accelerating changed everything. It suggested that gravity is not the only large-scale player in the story. Dark energy, or something behaving like it, appears to be pushing the cosmos outward in a way that makes recollapse harder. Under the simplest current models, this means the Big Crunch is not the leading expectation. And yet it has not disappeared completely from thought. Because dark energy remains mysterious. If its nature is more subtle than a simple cosmological constant, if it evolves over time, weakens, changes sign, or reveals new behavior on vast scales, then the future could still be different from the neat heat-death scenario. The universe we see now might be in a temporary phase of acceleration rather than a permanent one. If that were true, then gravity, or some deeper large-scale effect, might yet regain the upper hand. So the Big Crunch remains in the family of serious possibilities, not as the default answer, but as one of the most dramatic alternatives. And emotionally, it feels very different from the endings we have already visited. Heat death is the universe becoming too even to continue. The Big Rip is the universe becoming too unstable to hold together. The Big Crunch is the universe becoming too crowded to remain open. It is an ending by return. Let us imagine it slowly. Far in the future, the universe is still expanding, as it is now. Galaxies continue to move away from one another. Space stretches. Distances grow. But at some unimaginable epoch, something begins to change. The outward expansion no longer accelerates with the same confidence. Perhaps dark energy weakens. Perhaps its effect is not constant after all. Perhaps the overall dynamics of spacetime turn out to be more complicated than we currently think. However it happens, the important thing is that the expansion rate starts to slow. At first, this would be almost impossible to notice locally. The universe is too large, the timescales too vast, the processes too gradual. There is no giant lever in the sky visibly being pulled in the other direction. Instead, the outward drift of galaxies becomes just a little less strong than it would have been. The cosmos is still getting bigger, but the future no longer points cleanly toward endless separation. Then, after another age beyond easy comprehension, expansion stops. That moment is one of the most eerie in all of cosmology, not because it would feel dramatic in real time, but because of what it means. For the first time since the earliest history of the universe, the large-scale motion of the cosmos is no longer outward. The expansion rate reaches zero. Space is, for an instant in the broadest possible sense, neither growing nor shrinking. And then it begins to contract. This is where the emotional meaning of the Big Crunch truly begins. A universe that had spent billions upon billions of years becoming more spacious now turns inward. The distances between galaxies begin to decrease. Structures once fleeing one another start to approach. The future stops being about exile and starts being about convergence. At first, the reversal might even seem subtle. Galaxy clusters that had once drifted apart begin, very slowly, to close the gaps between them. Distant galaxies become less distant. The cosmic background radiation, which had long been stretched into colder and colder wavelengths by expansion, begins to compress and heat as the universe contracts. The overall temperature of the cosmos stops falling and starts rising. A chill that had defined the deep future slowly yields to warmth. The direction of history changes. That may be the simplest way to say it. A universe heading toward heat death tells a story of increasing isolation. A universe heading toward the Big Crunch tells a story of increasing encounter. Imagine a civilization, impossibly far in the future, if any such thing could exist during these epochs. For ages, its astronomers had watched the sky thin out. The universe seemed to be a story of things becoming unreachable. But now, with enough time and enough precision, they begin to notice something astonishing. The recession of distant structures has slowed. Light that should have stretched more quickly is not stretching as expected. The background glow of the universe is no longer fading in the same way. Over immense spans, the sky changes character. The cosmos is no longer leaving itself behind. It is preparing to come together. As contraction continues, the effects become less gentle. Galaxies that once drifted apart now move toward one another. The great dark spaces between clusters shrink. Collisions become more frequent. Mergers, which in an expanding universe eventually become rarer on the largest scales, now become inevitable again. The future grows busier, denser, more violent. This is one of the most visually striking differences between a crunching universe and a dying one under heat death. Heat death drains the sky. The Big Crunch refills it. But it does not refill it with peace. It refills it with impact. Galaxies crash into one another. Gas clouds collide and compress. New waves of star formation may ignite from the chaos as matter is forced into dense regions again. There is something darkly beautiful in that. A universe headed toward collapse may produce a strange late renaissance of fire, not because it is becoming young, but because increasing density gives gravity and pressure new ways to create light before the final end. So in one sense, the Big Crunch is less lonely than heat death. It is also much harsher. The age of contraction would not simply be a replay of the early universe in reverse, at least not in any neat cinematic way. Too much history has happened. Galaxies are no longer distributed as they were near the beginning. Stars have lived and died. Black holes have formed. Heavy elements are widespread. Structure is far more complicated. But the broad trend does reverse. Separation gives way to crowding. Cooling gives way to heating. Expansion gives way to inward motion. As the universe becomes smaller, radiation becomes more energetic. Collisions become more common. Matter encounters matter not after drifting apart, but after being driven back together by the shrinking of space itself. Over still longer timescales, the entire cosmic environment grows hotter and denser. This is where the Big Crunch begins to feel almost apocalyptic in the old religious sense, not because it is moral, but because it is total. There is no quiet place to hide from a contracting universe. This is not a local disaster like a star-going supernova or a galaxy merger disrupting one region of the sky. It is the global condition of space-time becoming less hospitable everywhere. The whole stage is tightening. Picture the future now. Galaxies that were once independent have merged into larger and larger structures. Black holes, especially supermassive ones, become more significant because dense matter is everywhere more likely to fall inward. Radiation fills space more intensely. The night sky, if night still has meaning, is no longer sparse or calm. It glows with the crowded violence of a universe under compression. Stars may be born again in abundance for a while from the dense gas driven into collapse, but this is not a stable new golden age. It is the brightness of a furnace being sealed shut. The renewed light belongs to the approach of a greater confinement. It is the flare before the crush. And as the contraction continues, even ordinary stars become less important than the rising background itself. The universe as a whole grows hotter. This is crucial. Heat death ends in low temperature and uniformity. The Big Crunch ends in high temperature and uniformity of a very different kind. In the final stages, the cosmos is no longer a scattering of hot objects in cold emptiness. It becomes a dense thermal environment where space everywhere is infused with extreme energy. The difference between objects and background begins to blur. Matter as we know it may not survive those final conditions. At high enough temperatures and densities, atoms cannot remain intact. Electrons are not held in ordinary orbits. Nuclei themselves are threatened. The very forms of matter familiar to chemistry and life dissolve into more basic states. The later the crunch proceeds, the less recognizable the universe becomes. There is something almost mercifully abstract about that. Long before the final singular conditions, the universe would already have ceased to be a place for observers like us. Worlds, stars, galaxies, and the calmer scales of existence would have been swallowed into the compression. The final approach belongs not to biological imagination, but to plasma, radiation, gravity, and whatever physics rules matter at the highest densities. And then comes the deepest question. What happens at the end of the Big Crunch? In the simplest image, everything collapses toward a final singularity, a state of infinite density and temperature, where the mathematics of general relativity breaks down much as it does at the beginning of the Big Bang. Space shrinks. Energy density rises without bound. The known equations stop being reliable guides. In that sense, the Big Crunch is not merely an ending. It is a place where our current physics reaches its edge. That edge is one reason the scenario fascinates people. A singularity is not just a dramatic final object. It is a sign that our understanding is incomplete. It is nature telling us that the conceptual tools we are using have gone as far as they can go. Beyond that, we need something deeper, perhaps a full theory of quantum gravity, to say what reality is really doing. So when we speak of the Big Crunch, we are speaking partly in known physics and partly at the border where known physics becomes uncertain. And uncertainty opens another door. Because if the universe really did collapse back into an ultra-dense state, could that be the end of everything, or could it become the beginning of something else? This is where the idea of the Big Bounce enters the story. The Big Bounce is the possibility that a contracting universe does not end in a final dead singularity, but instead reaches some maximum density and then rebounds. In that case, the Big Crunch would not be the absolute end. It would be a turning point. The collapse of one cosmic cycle would become the birth of another. A new expansion would follow. Another Big Bang, not from nothing, but from the compressed remains of a previous universe. This idea is deeply appealing, both scientifically and emotionally. It offers a way around the singularity problem. It replaces absolute beginning and absolute ending with cycles. It turns the universe into something rhythmic. Expansion, contraction, bounce, expansion again. There are various theoretical models in which something like this could happen. Some come from loop quantum cosmology, some from Bryn world ideas, some from other speculative approaches to early universe physics. None is confirmed, but they show that the Big Crunch is not always imagined as the final full stop. Sometimes it is imagined as a comma. Still, it is important not to smooth away the violence of the collapse simply because a bounce is imaginable. Even if another universe were to emerge, the one we know would still be gone. All present structures, all galaxies, all stars, all planets, all observers, all histories, all memories, would be crushed beyond recognition. A bounce, if it exists, would not preserve the familiar. It would only preserve existence in some more abstract sense. It would be continuation without continuity. That may be even stranger than a clean ending, because it means reality might survive while everything we mean by our universe does not. There is also a philosophical beauty to the symmetry between the Big Bang and the Big Crunch. The universe begins in density and heat, and in this scenario ends in density and heat. But the two are not the same kind of moment. The beginning is full of potential. The end is full of history. The beginning is simple because nothing has yet had time to form. The end is simple because everything has been forced back through the collapse of complexity. Those are very different simplicities. One is innocent. The other is exhausted. If you sit with that long enough, the Big Crunch starts to feel less like a disaster movie and more like a tragic return. Not a happy homecoming. Not a neat reset. But a deep cosmic folding. The universe, after spending unimaginable ages making room for stars, planets, life, black holes, emptiness, and possibility, gathers all of that back inward until no separate thing can remain itself. A universe under contraction is a universe losing its distance. And distance, in many ways, is what made the whole story possible. Space between stars allowed solar systems to form. Space between galaxies allowed structure to emerge. Space between particles allowed matter to cool and settle into atoms. Space made room for time to express itself as complexity. The crunch takes that room away. Bit by bit, then all at once. This is what makes it the opposite of heat death in the deepest sense. Heat death is the exhaustion that comes from too much room. Everything is too spread out, too isolated, too diluted to keep happening. The Big Crunch is the exhaustion that comes from losing room entirely. Everything is too crowded, too hot, too compressed to remain distinct. In one future, the story thins out. In the other, it collapses in on itself. And somewhere between those two possibilities lies one of the most unsettling truths in cosmology. The universe does not promise that reality will remain habitable just because it has been habitable for a while. It does not promise that expansion will continue forever in one familiar mode. The deep future may be shaped by rules or changes we do not yet fully understand. Dark energy, gravity, quantum behavior, and the geometry of space-time still hold secrets from us. That uncertainty is not a weakness in the story. It is part of what makes the story alive. Because the future of the universe is not a solved riddle. It is an open one. And as if the quiet fate of heat death, the tearing violence of the Big Rip, and the collapsing furnace of the Big Crunch were not enough, there remains one more possibility, perhaps the most unnerving of them all. Not because it is the loudest, not because it takes the longest, but because it could, in principle, happen without warning. A failure not of stars, or gravity, or expansion, but of the vacuum beneath reality itself. In the next part, we turn to vacuum decay, the idea that the universe may be balanced on a false floor, and that one quantum event somewhere in the dark could rewrite the laws of physics faster than any signal could ever warn us. Vacuum decay. In the next part, we turn to vacuum decay, the idea that the universe may be balanced on a false floor, and that one quantum event somewhere in the dark could rewrite the laws of physics faster than any signal could ever warn us. Of all the endings we have visited so far, this may be the most unsettling. Not because it is the loudest, not because it is the most visually spectacular, not because it waits patiently at the end of trillions upon trillions of years. In fact, vacuum decay is frightening for almost the opposite reason. It does not necessarily arrive after the stars are gone, or after black holes evaporate, or after the universe has had time to grow old with dignity. It could, in principle, happen long before any of that. Long before heat death. Long before a Big Rip. Long before a Big Crunch could gather the cosmos back into fire. It could happen in a universe that still looks calm. A universe with galaxies. A universe with stars. A universe with planets, oceans, and people who think they still have time. That is what gives vacuum decay its peculiar chill. The other endings feel like futures. This one feels like a trapdoor hidden beneath the present. If you enjoy these calm journeys into the deeper edges of physics, you can gently leave a like, subscribe if you want more slow science stories like this, and if you feel like it later, tell me in the comments which kind of ending feels more haunting to you, one you can see coming across ages, or one that arrives with no warning at all. For now, let us move carefully into one of the strangest ideas modern physics has ever allowed. To understand vacuum decay, we first have to let go of a very ordinary assumption. The assumption is that empty space is simple. We have already touched on this idea when talking about black holes and Hawking radiation. In everyday life, emptiness feels like the absence of things. If a room is empty, it contains no furniture. If a bottle is empty, it contains no water. If intergalactic space is empty, we imagine a vast nothingness between the stars. But physics is not so easily satisfied by the word nothing. Empty space is not merely a passive backdrop where things happen. In modern quantum field theory, space is filled with fields, and particles are excitations of those fields. The electron field is everywhere. The quark fields are everywhere. The electromagnetic field is everywhere. Even in a perfect vacuum, what we call empty space still has structure, rules, energy properties, and a very deep importance to the shape of reality. This means the vacuum is not just blankness. It is a condition, a state, and like all states in physics, it may or may not be stable. That is where the story begins. When physicists talk about vacuum decay, they are asking whether the vacuum state of our universe, the particular configuration of fields that currently gives nature its familiar properties, is truly the lowest possible state, or only a temporary one. In more intuitive language, they are asking whether reality is resting at the bottom of the deepest valley available, or whether it is merely sitting in a shallow valley while a deeper one exists somewhere beyond a hill. This is often illustrated with the image of a landscape. Imagine a hilly terrain in fog. A ball rolls downhill and settles into a valley. From where it sits, everything seems stable. It is no longer moving. It has found a low point. But unknown to the ball, beyond a nearby ridge lies a much deeper valley. The ball is not in the true lowest state. It is in a false minimum, a place that is locally stable but not absolutely stable. If some disturbance gives it enough opportunity, or if quantum mechanics allows the right kind of tunneling event, the ball can cross the barrier and fall into the deeper valley. When that happens, its position changes suddenly and fundamentally. What once looked like a comfortable resting place is revealed to have been temporary all along. That is the essence of the false vacuum idea. Our universe may be the ball. And the field most often discussed in this context is the Higgs field. The Higgs field is one of the most important ingredients in modern physics because it is tied to why certain particles have mass. It is not something added later like decoration. It is part of the underlying arrangement of reality. The famous Higgs boson, discovered at CERN in 2012, was one of the great triumphs of modern science because it confirmed that this field is real. But once the Higgs boson was discovered and its mass was measured more precisely, something interesting and slightly unsettling emerged. According to some calculations, using the measured values of the Higgs boson mass and the top quark mass, our universe may sit in a vacuum state that is not perfectly stable. It may be metastable. Metastable is one of those gentle scientific words that hides a great deal of drama. It means stable enough for now. Stable enough to last a very long time. Stable enough that the universe can contain galaxies, stars, chemistry, and life. But not necessarily stable forever. A false floor that can hold you for billions of years is still a false floor. Now, this is where care matters. The calculations involved are subtle. They depend on measured particle masses, on how the Higgs field behaves at very high energies, and on whether there is other undiscovered physics beyond the standard model that changes the picture. So vacuum decay is not a confirmed forecast. It is a serious possibility emerging from the mathematics we currently know, but it comes with uncertainty. The standard model alone hints at metastability, but new physics could stabilize everything. Or our interpretation could change with better measurements. Still, the possibility remains disturbing because of what it implies if it is true. If our vacuum is only metastable, then there may exist a lower energy vacuum state, a true vacuum, that the universe could in principle transition into. And if that transition starts anywhere, it does not stay local. This is where vacuum decay stops sounding like a technical curiosity and starts sounding like one of the most terrifying ideas in cosmology. Suppose somewhere in the universe, through an incredibly rare quantum event, a tiny bubble of true vacuum appears. Not because of a star exploding, not because of an alien machine, not because of some external force acting on the cosmos. Simply because quantum physics sometimes permits tunneling between states. The fields in one tiny region find a way to slip from the false vacuum to the true one. That bubble would not just sit there quietly. It would expand. And it would expand at very nearly the speed of light. Why? Because the true vacuum is a lower energy state. Once a patch of the universe falls into it, the surrounding false vacuum becomes unstable against it. The boundary of the bubble moves outward, converting more and more of space into the new vacuum. The process feeds itself. The lower energy state wins because physics favors it once the transition has begun. And the most unsettling detail of all is this: you would not see it coming. If the bubble wall expands at the speed of light, then no information can outrun it. No warning signal can arrive first. No telescope can show it approaching in time to matter. No alarm could ever ring. There is no moment of watching doom cross the sky from a safe distance. There is no preparation. One instant, the old laws of physics still govern your region of space. The next, they do not. This is very different from every other cosmic ending we have discussed. Heat death can be understood as a long exhaustion. The Big Rip unfolds in stages. The Big Crunch develops over immense eras of reversal and collapse. Even black hole evaporation, for all its mystery, is patient almost beyond thought. Vacuum decay, by contrast, hides inside normality until the moment normality is over. That is why it feels so intimate and so cold. A star gives hints when it is dying. A galaxy merger leaves signs. The expansion of the universe can be measured. But vacuum decay offers no visible prelude. The world does not darken first. The sky does not redden. There is no cosmic drumroll. Reality is simply replaced. To understand why this replacement is so complete, we need to think about what a different vacuum state would actually mean. The vacuum is not just empty space in the casual sense. It helps determine the behavior of the fields that govern particles and forces. If the vacuum state changes, then the basic constants and relationships that make matter possible may change with it. Particle masses could become different. Forces could have different strengths. Atomic structure might no longer be possible in the way we know it. Chemistry could fail. Stable nuclei might cease to exist. The very patterns that allow stars, planets, molecules, cells, and thoughts to emerge might not survive the transition. This means the bubble of true vacuum is not just a region of space with a different mood. It is a region with different physics. And the difference may be fatal to everything that presently exists. That does not necessarily mean the new vacuum is chaotic or violent from the inside. It may be perfectly orderly according to its own rules. But those rules would not be ours. The universe we know would not continue within it. The structures built under the current vacuum would be erased because the ground under them, in the deepest possible sense, had changed. Imagine writing a long novel on paper, only to discover that the paper itself can suddenly turn into water. The story is not erased by someone crossing out the words. It is erased because the medium that made the words possible has changed state. Vacuum decay is like that. Reality is not destroyed by collision. It is invalidated by a new underlying condition. There is another subtle reason the idea feels so unsettling. It does not rely on cosmic scale in the usual way. Heat death needs immense time. The Big Rip requires the long behavior of dark energy. The Big Crunch depends on the fate of expansion across the whole universe. Vacuum decay begins small. A microscopic bubble, a quantum event, a tiny seed. Something almost nothing-sized. And yet, if the conditions are right, that tiny event is enough to rewrite everything. There is a grim elegance in that. The greatest catastrophe does not begin with the largest object. It begins with a shift in the vacuum, a change so fundamental that size becomes secondary. Smallness is no protection from importance. Now, one natural question is whether some energetic event, like a powerful collider or a cosmic ray, could trigger vacuum decay artificially. This concern has appeared from time to time in public discussions, especially around particle accelerators. But physicists have generally reassured us on this point for a very good reason. The universe is already filled with extremely high-energy cosmic rays, some of which are far more energetic than anything we have produced in laboratories. They have been colliding with particles in Earth's atmosphere, on stars, on dead worlds, and across the cosmos for billions of years. If such collisions were likely to trigger vacuum decay, the universe would probably have already done it many times over. So the danger, if it exists, is not something our machines are uniquely summoning. It is simply built into the question of whether the vacuum is truly stable. And that brings us to the strangest emotional feature of the whole idea. Vacuum decay may be possible, but it may also be so fantastically improbable that the universe can continue in its metastable state for a time far longer than any other relevant cosmic timescale. In many calculations, the expected lifetime of such a vacuum is vastly greater than the current age of the universe, and perhaps greater than the timescales associated with stars, proton decay, and even black hole evaporation. In that sense, metastable does not mean fragile in any ordinary way. It means only that forever may not be literally forever. A glass can sit on a shelf for years. Metastability is the cosmic version of that glass sitting there for ages beyond imagination, while still not being the deepest available state. The probability of transition in any given moment may be absurdly low. And yet a low probability is not zero. That is enough to keep the idea alive in the scientific imagination. There is also a beautiful and eerie connection here to the earliest universe. In some models of cosmic inflation, the infant universe may itself have undergone vacuum transitions. The early cosmos may have been shaped by scalar fields sitting in high-energy states and then relaxing into lower ones, driving expansion and setting the conditions for the hot Big Bang that followed. So vacuum structure is not just a speculative doom mechanism. It may be deeply tied to why the universe exists in its present form at all. That adds another layer of strangeness. The same general kind of physics that may have helped make our universe habitable could also contain the possibility that habitability is temporary. Reality may owe its history to vacuum transitions and remain vulnerable to them. When you sit with that for a while, the universe starts to feel less like a rigid machine and more like a landscape of temporary settlements. Stable enough to build galaxies. Stable enough to grow life. Stable enough to write history. But beneath it all, perhaps not perfectly final. This is where vacuum decay becomes more than a scary thought experiment. It becomes a meditation on what we really mean by stable. We tend to call something stable when it lasts longer than we do. Mountains are stable relative to a person. Continents are stable relative to a civilization. Stars are stable relative to species. But physics asks the question more strictly. Stable means lowest, permanent, not just long-lasting, but incapable of falling further. Metastable means something else. It means a peace that endures without being ultimate. A calm that is real, but conditional. That is a deeply human kind of idea too, and perhaps that is why it lingers in the mind. Much of life feels stable because it lasts long enough to hold memory, culture, identity, and continuity. But many forms of stability are only local. They hold until something deeper shifts. Vacuum decay takes that ordinary intuition and places it beneath the whole universe. One of the most haunting images in all of cosmology is therefore not a black hole or a supernova or a torn galaxy. It is a bubble. A bubble of true vacuum silently expanding through the dark, invisible until it arrives, carrying with it a different version of the laws of nature. Not a weapon, not a fire, a correction. Reality deciding, in one region after another, that its previous arrangement was not final. And because the bubble wall moves at the speed of light, there is almost no meaningful sense in which an observer could contemplate it from outside. If it comes as the end of contemplation itself. No fear in advance. No strategy. No final human moment of understanding. The old universe simply ceases to apply. There is, strangely, something almost merciful in that. Not because the event is good, but because it would leave no time for dread. Heat death lets you imagine the long sadness of old age. The big rip lets you imagine the sky coming apart. The big crunch lets you imagine the universe heating into furnace-bright collapse. Vacuum decay denies even the long emotional preparation. It is the quietest kind of finality. Now, scientifically, it is worth repeating that we do not know whether vacuum decay will happen. We do not even know for certain whether our vacuum is metastable in the relevant sense once all unknown physics is included. The Standard Model hints. Measurements point intriguingly. But new particles, new interactions, or deeper theories could change the conclusion. The universe may be safer than the most unnerving reading suggests. Still, the fact that serious physics can even formulate the idea is extraordinary. It means that the final fate of the universe may depend not only on stars and gravity and expansion, but on the deep architecture of quantum fields. It means cosmology and particle physics are not separate stories. The fate of everything large may depend on the properties of the very small. That is one of the great lessons of modern science. The universe is unified in its strangeness. A particle mass measured in a collider can whisper about the destiny of galaxies. A field permeating empty space can decide whether chemistry lasts forever. A quantum event in one tiny region could, in principle, rewrite the laws governing the whole observable cosmos. There is a grandeur in that, even if it is unsettling. And perhaps that is what makes vacuum decay such a fitting near-final chapter in our journey. We began with stars, galaxies, entropy, and dark energy. We moved through black holes, heat death, tearing space, and collapsing universes. And now, as we approach the deepest question of all, what the last second of reality might truly mean, we find that reality itself may be less solid than it appears. Not fragile in the everyday sense, but provisional. That is the word that hovers over vacuum decay. Provisional stars, provisional atoms, provisional skies, provisional laws. The world feels permanent because it has been consistent for billions of years. But consistency is not the same as necessity. A pattern can hold for an immense span and still not be ultimate. If there is any comfort here, it may lie in the scale of uncertainty. Vacuum decay is not something we have evidence is imminent. It is a theoretical possibility, one of the universe's darker options, not a countdown written on the wall. The sky tonight is still the same sky. Stars still shine by the old rules. Matter still holds together. The Higgs field still grants mass in the familiar way. Whatever the ultimate truth of vacuum stability is, it has not yet interrupted the story. And that means we still live inside a working cosmos. Perhaps that is the right place to pause before our final part. Because by now we have walked through almost every major ending modern cosmology allows us to imagine. The universe may fade into heat death. It may tear itself apart in a big rip. It may collapse in a big crunch. It may be rewritten by vacuum decay. Each possibility gives us a different answer to the same ancient question. How does reality stop being what it is? And in the next and final part, we gather all of these endings together and return to the image that began this whole journey, the last second of the universe. Not just one theory, but the deeper question beneath them all. What would the final moment of reality really mean? Could anything witness it? Would time still have meaning there? And does the universe, in any sense at all, notice its own ending? The last second of reality. And in the next and final part, we gather all of these endings together and return to the image that began this whole journey, the last second of the universe. Not just one theory, but the deeper question beneath them all. What would the final moment of reality really mean? Could anything witness it? Would time still have meaning there? And does the universe, in any sense at all, notice its own ending? That is where we have arrived now. After all the stars, all the black holes, all the slow cooling and violent tearing and collapsing possibilities, we are left with one final question that is not only scientific, but strangely intimate. If the universe has an ending, what is an ending like when it happens to everything? Not the end of a city, or a species, or a planet, or even a galaxy. The end of the stage itself. The end of the background that made every other event possible. There is something difficult about even trying to imagine it, because our minds were built inside change. We understand endings by contrast. Day ends because night begins. A life ends because others continue. A fire ends because the room remains. But the end of the universe, or the end of the form of reality we know, is different. There is no outside room waiting for the smoke to clear. There is no larger human context holding the event in place. When reality itself changes beyond recognition, or falls silent, or tears apart, the meaning of a final moment becomes much harder to hold. And yet we keep asking, We keep asking because human beings have always been creatures who look beyond the horizon. We ask where things came from. We ask where they are going. We ask what remains when the lights go out. And perhaps most of all, we ask whether there is any final shape to the story at all, or whether reality only changes costumes forever. If these slow cosmic journeys help you unwind, you can gently leave a like, subscribe if you want more calm science stories like this, and if you feel like it after we reach the end, tell me in the comments which fate for the universe feels most convincing to you, or perhaps most haunting. For now, let us keep going. One last time. We have already seen that there may not be one single answer to how reality ends. Under the most familiar modern picture, the universe expands forever. Stars burn out. Galaxies slip beyond one another's horizons. Black holes evaporate. The cosmos approaches heat death, a state of maximum entropy in which useful energy differences are gone and almost nothing meaningful can happen anymore. In that scenario, the end is not a sharp event. It is a fading. The last second is poetic, not literal. The story becomes so quiet that it effectively ends, even if time, in some formal sense, continues. But under other possibilities, the ending is more violent. If dark energy grows stronger with time, the universe could face a big rip. The largest structures would fail first, then galaxies, then solar systems, then planets, then matter itself. In that future, the last second may be much closer to what the phrase suggests, a genuine terminal instant in finite time, a point beyond which no stable structure survives. There, the last second of reality would be the last second in which anything can remain assembled. If cosmic expansion someday reverses, then the universe could move toward a big crunch. The distances between galaxies would shrink. The cosmos would heat up. Matter would be driven together into denser and denser states. If such a collapse ends in a true final singularity, then the last second is the final approach to compression beyond our current understanding, the last interval in which the universe remains extended at all before collapsing into a condition our physics cannot fully describe. And if vacuum decay is possible, the ending may not wait for deep time. It may not care about the patient aging of stars or the slow mathematics of entropy. A bubble of true vacuum could form and expand at the speed of light, rewriting the laws of physics as it moves. In that case, the last second is not cosmic old age. It is the last second before the local rules that make matter, chemistry, and thought possible are replaced. So which is the real last second? The honest answer is that we do not yet know. That may sound unsatisfying at first, but it is also part of what makes cosmology so beautiful. We are not standing at the end of knowledge. We are standing inside a living question. We know enough to sketch possibilities, enough to rule some out as unlikely, enough to see the broad logic of entropy, dark energy, gravity, and quantum fields, but not enough to say with perfect confidence how reality ends. Still, even within that uncertainty, something deeper becomes visible. In every scenario, the ending is not simply about destruction. It is about the loss of the conditions that made familiar existence possible. That is the thread running through everything. In heat death, the conditions for work and structure disappear. In the Big Rip, the conditions for binding disappear. In the Big Crunch, the conditions for separation disappear. In vacuum decay, the conditions for our version of physics disappear. The universe may end in different ways, but every ending is, at heart, the undoing of what once allowed stars, planets, chemistry, memory, and life to happen. That is why the question feels larger than astronomy. It reaches into philosophy, identity, and time itself. Because once you start asking about the last second of reality, you are really asking something more personal too. What makes a world a world? Is it matter? Is it structure? Is it law? Is it the presence of observers? Is it the possibility of change? When enough of those vanish, at what point do we say the universe is still here, but the story has ended? Take heat death, for example. In a strict physical sense, the universe still exists afterward. There are still particles, fields, photons stretched to immense wavelengths, and the continuing expansion of spacetime. But if nothing meaningful can happen, if there are no stars, no black holes, no free energy gradients, no chemistry, no memory-bearing structures, then in another sense the universe has already passed beyond what we emotionally recognize as reality in action. The book remains on the table, but no new pages are being written. In that case, perhaps the last second is not the final instant of existence, but the final instant of meaningful becoming. That is a very different kind of ending. And it leads to another question that has hovered quietly beneath our whole journey. Could anything witness the end? It is a simple question on the surface, but it becomes very strange very quickly. Because witnessing requires more than eyes. It requires structure. It requires memory. It requires an observer whose internal order can persist long enough to register a before and an after. A witness must be a system that changes in relation to what it sees. In other words, witnessing depends on exactly the sort of organized, energy-using complexity that the late universe gradually destroys. In the heat-death scenario, this is especially important. As the universe ages, useful energy becomes rarer and rarer. The kinds of processes that support life, computation, and sustained memory become harder to maintain. Eventually, whatever observers might once have existed would face a universe increasingly hostile not through violence, but through scarcity of meaningful gradients. There may come a stage long before the deepest final silence when witnessing itself becomes impossible. Not because the universe has ended yet, but because the observer has. The same broad problem appears in the other scenarios too. In a big rip universe, once galaxies and solar systems start to fail, local observers lose the environmental stability required to continue existing. In a big crunch, the growing density and temperature make large-scale complexity harder and harder to sustain. In vacuum decay, the change arrives too fast for warning or reflection. In every case, the conditions for witnessing seem to disappear before or at the same time as the condition being witnessed. This means the last second of reality may not be seen by anyone at all. It may be a final threshold without an audience. That thought can feel lonely, but it also carries a strange purity. The universe does not require witnesses in order to be real. Stars burned for billions of years before eyes existed to see them. Galaxies collided long before minds appeared to imagine them. The final moments of reality may pass in the same way, not because they are small or unimportant, but because they belong to physics first, and only to consciousness by temporary accident. Still, there is a softer version of the question worth asking. If no one can witness the final second itself, could there be minds earlier in the story that understand, at least approximately, what is coming? That is the position we are in now. We may never stand at the literal edge of the universe's final moment, but we can think toward it. We can model it. We can tell stories about it. We can place ourselves, through imagination and mathematics, in futures we will never physically inhabit. And that may be one of the most remarkable things about consciousness. It does not need to survive until the end in order to participate in the meaning of the end. It can reach forward conceptually. The universe, at least in one small place and for one brief span, became able to wonder about its own fate. That matters. It matters because it changes how we think about scale. The timescales we have walked through are so enormous that human history vanishes inside them. Civilizations are nothing next to stellar lifetimes. Stars are brief next to the red dwarf era. The age of stars is tiny next to black hole evaporation. A Google years makes almost every other number feel decorative. By comparison, our lives are less than instants. And yet, instants can understand astonishing things. A being who lives for only decades can grasp billions of years. A species only recently aware of the wider cosmos can infer the fate of stars, black holes, and perhaps the universe itself. That is not a small achievement. That is one of the grandest things the universe has ever produced, a temporary structure capable of understanding long-term reality far beyond its own survival. So no, perhaps nothing will witness the final second directly. But something has already begun to understand what such a second might mean. And maybe that is enough to give the question a kind of dignity. There is another mystery here too, one that becomes more philosophical the longer we sit with it. Would time still have meaning at the end? This question comes up most often in the heat-death scenario, because that ending is defined by the thinning out of events. If time is just a coordinate in an equation, then yes, time can still continue in some formal sense. One moment can still follow another. Expansion can still proceed. A wavelength can still stretch. A particle can still drift. Physics can still use the symbol. But human beings do not experience time as a symbol. We experience it through change. Morning becomes afternoon because light moves. A year passes because seasons return. A memory becomes old because new memories replace it. A song unfolds because one note gives way to the next. Time, in lived experience, is inseparable from sequence, from contrast, from process. When those thin out enough, time stops feeling inhabited. It becomes abstract, not absent, but strangely hollow. A heat-dead universe may therefore still have time without having what we emotionally mean by history. There is a difference. History is time filled with change that matters to structure. In the deepest future, there may be time but no history. That thought alone can keep the mind awake, if one lets it. And yet even in more dramatic scenarios, time becomes fragile near the end. In a big rip, as structures fail at every scale, the ordinary clocks of reality fail too. A year, a day, an orbit, a stable system, these all depend on binding and repetition. In a big crunch, as density rises and the cosmos approaches conditions beyond our current theories, time as described by general relativity reaches territory where our mathematics becomes uncertain. In vacuum decay, the concept of before and after inside the changed region may no longer map cleanly onto the old laws that gave meaning to the question. So perhaps the last second of reality is also the last second in which time still feels like something familiar. That is a profound kind of ending. Not just the end of matter or stars, but the end of a recognizable flow. There is also one final question, quieter than the others, but maybe the most haunting. Does the universe notice its own ending? At first, that sounds like a poetic question rather than a scientific one, and in one sense it is. The universe, as far as we know, is not a mind floating above itself, waiting to observe its own final page. It has no central observer, no cosmic face turned inward. Physics does not suggest that reality as a whole possesses a single perspective. And yet the question remains strangely hard to dismiss. Because for at least one brief interval, in one small region, the universe produced beings who could notice it. It produced stars, and from stars elements, and from elements worlds, and on one of those worlds, minds. Minds that asked where the universe came from. Minds that measured its expansion. Minds that imagined its death. In that limited and fragile sense, the universe has already noticed itself. Through us. Through anyone, anywhere, who has ever looked at the night sky and wondered what it all means, or how it all ends. That may be the closest thing the cosmos ever has to self-awareness. Not a permanent feature. Not something guaranteed in every age. Just a brief flowering of reflection inside a larger process that is otherwise silent. And if that is true, then perhaps the most astonishing part of the whole story is not the last second itself. Perhaps it is the fact that before the last second, there was a middle in which the universe could ask about its own fate. A warm interval. A thinking interval. A narrow window in cosmic history when matter was arranged just right for questions. That does not solve the problem of endings, of course. It does not stop the stars from dying or the entropy from rising. It does not protect galaxies from expansion or black holes from evaporation. It does not stabilize a possibly metastable vacuum, but it gives the story a kind of inwardness it would otherwise lack. The universe is not just happening in one small corner, it is being understood. And perhaps that is enough to change the emotional shape of the end. Because when people hear about cosmic endings, they often feel a certain despair. If everything vanishes, what does anything mean? If the stars die, if black holes fade, if even the laws of physics could shift, then what is the point of all this brief beauty? But maybe that question is too tied to permanence. A song does not need to last forever to be real. A sunrise does not need to happen without end to matter. A life does not need to be infinite to contain meaning. Meaning may not come from escaping endings. It may come from being able to exist, to feel, to think, and to understand inside a universe where endings are possible at all. That is not a sentimental answer. It is almost the opposite. It is an answer built on fragility. The stars matter because they do not last forever. The age of galaxies matters because it is temporary. This moment of cosmic history matters because it is rare. And consciousness matters because it arises briefly between a violent beginning and an uncertain end, and still somehow manages to ask what the whole thing means. When you look at the story that way, the last second of the universe becomes less like a threat hanging over the present and more like the far edge that defines the shape of the whole journey. The final line gives the earlier chapters their contour. The fact that reality is not guaranteed forever makes every temporary form inside it more astonishing, not less. A planet with oceans, a sky with stars, an element forged in a stellar core, a thought occurring in the dark. These are not diminished by impermanence. They are intensified by it. Still, the science remains what it is. The future is uncertain. Heat death remains the broad leading picture under current cosmology, but dark energy still hides its full nature from us. The Big Rip is possible in some models. The Big Crunch lingers as a revived alternative if cosmic acceleration changes character. Vacuum decay remains one of the strangest quantum possibilities in the background of particle physics. The universe has not yet told us which ending belongs to it. Perhaps that uncertainty is fitting, because the deepest truths are often not the ones that close the book cleanly, but the ones that keep us honest about how much remains unknown. We know enough to be humbled, enough to be amazed, enough to see that reality is larger, older, and stranger than anything our ancestors could have imagined under the first night sky. And maybe that is the real gift of asking about the final second. Not the ability to predict every detail, but the ability to feel the scale of existence more clearly. To understand that we live in a very brief, very precious interval when stars still shine, matter still gathers into living forms, and the universe is still open enough to be studied by minds like ours. One day, whatever ending is true, that interval will be over. The stars will not burn forever. The black holes will not endure forever. Even the vacuum may not be eternal in the way we casually assume. But for now, the universe is still in progress. For now, the night sky still holds its old lights. For now, there are still planets warm enough for oceans, enough chemistry for life, enough structure for memory, enough silence for wonder. And that may be the gentlest conclusion we can arrive at after walking all the way to the edge of time. The last second of the universe may come as a whisper, a tearing, a collapse, or a silent correction of reality itself. But before that last second, there is this brief bright middle, this age of stars, this moment when the cosmos is still unfinished, and somewhere inside it, a mind can look outward into the dark and ask how the story ends. And perhaps, for now, that is more than enough.